Every star you've ever seen, every myth, every map, every wish, lives inside one vast spinning city of gravity, and we're trapped in its streets. Yet for all our telescopes, we still can't agree on what our own galaxy looks like from the outside. So what is the Milky Way really? Its true shape, its hidden matter, its violent past and its fate, and how do we prove it from inside the dust and dark? The Milky Way is not a picture in a book. It is a moving labyrinth of light, gas, and time, and the deeper we measure, the more the galaxy answers with shadows. Our evidence arrives warped by dust, stretched by distance, and disguised by motion, yet it is enough to build a galaxy. Every photon and radio wave we collect is a clue recovered from inside the crime scene, where the walls keep shifting. We live among spiral tracers and star clouds, but the true architecture hides in statistics, spectra, and patient geometry. So this documentary follows a simple wager, that careful measurements can reveal the Milky Way's real design. Not as a clean portrait, but as a tested model, revised whenever new surveys sharpen the map. We will treat starlight like a language, where colour is chemistry, and brightness becomes distance only after corrections. We will track the galaxy's motions, subtle drifts across the sky, and Doppler shifts that turn velocity into structure. We will listen in radio, where hydrogen whispers at 21 centimetres and dust stops pretending it is a wall. And we will move through infrared, where crowded regions emerge and the centre's glare becomes readable rather than blinding. Along the way, the Milky Way will stop feeling like scenery and start behaving like a machine with competing parts. A thin disk forming stars today, a thicker, older disk carrying memory, and a bulge reshaped by a rotating bar. Above and beyond it all, a halo, faint, vast, and decisive, holds streams, clusters, and most of the mass. Some of what governs this system does not shine at all, yet it leaves fingerprints on every orbit we can measure. We will follow those fingerprints through stellar migrations, warped outer regions, and the strange calm of nearly flat rotation. Then the story tightens, toward the inner few light years, where gravity becomes extreme and time itself runs differently. There, stars race on tight paths that can be timed like clockwork, and the central engine reveals its weight. But the Milky Way is also a cannibal, still growing, still rearranging, through captured dwarfs and shredded debris. In the faint outskirts, ancient mergers survive as patterns in motion, and chemistry preserves a record older than the Sun. Even the gas between galaxies matters, because it feeds the disk, powers winds, and decides how long starbirth can continue. So we will ask what our galaxy is made of, how it assembled, and what forces will reshape it next. We will not claim certainty where the data refuses it. Some boundaries remain blurred by dust, bias, and the limits of our tools. Yet the deeper truth is stranger. From this interior vantage, we can still reconstruct a system, tens of thousands of light years wide, across 200 fascinating facts. Each one becomes a stepping stone, small, precise, and quietly astonishing. Because the Milky Way is not a backdrop to human history. It is the larger history we're trying to read. And the closer we read it, the more it feels alive, evolving, self-regulating, and keeping secrets in plain view. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. First we build the galaxy from the ground up, then we attempt its blueprint, then we weigh its invisible power. After that we enter its star factories, descend to its dark heart, trace its stolen past and look ahead to its fate. Look up on a clear night and you see a sky that feels infinite and open, as if it has no walls. Yet every naked eye star belongs to one gravitational system we cannot step outside, not even in imagination. That is the central paradox of the Milky Way. Our home is also our horizon, and the horizon is inside the home. We live inside it, so our view is warped by dust, distance, and motion, and even by the limits of our own eyes. We try to sketch a city while standing in its crowded streets, where the tallest buildings hide one another. The Milky Way is not the whole universe, and it is not a simple pinwheel frozen in place. It is one galaxy among hundreds of billions, shaped by dark matter, angular momentum, and the slow arithmetic of cosmic time. It is a barred spiral galaxy, meaning a flattened disk with spiral structure, plus a central bar of stars that rotates as a coherent feature. Around that bright centre sits a bulge, a thicker swarm of older stars with orbits that are less orderly than the disks. Beyond the disk lies a halo, a vast, sparse envelope of stars and globular clusters that marks ancient phases of assembly. Even farther out, an invisible halo of dark matter dominates the mass and sets the galaxy's gravity, like a scaffold you can't see but cannot ignore. From the ground, the Milky Way first arrives as a pale band across the sky, chalky and soft-edged. That band is mostly unresolved starlight packed along the disk's plane, so dense that the eye blends it into a continuous glow. Dark lanes cut through it because interstellar dust blocks visible light, and the dust grains are efficient at scattering blue wavelengths. In long exposure photography, those lanes look like ink poured into the starfield, branching, braided, and uneven. The band looks brighter in some directions because we look toward denser starfields, not because the galaxy is brighter there in any simple sense. When we face the inner galaxy, we look through more stars and more dust, so brightness and obscuration rise together. When we face outward, the glow thins and the lanes soften, and the star clouds feel more delicate. The light we see is not just stars, but a mixture of stellar populations layered along the line of sight. Some of that glow comes from relatively nearby stars in our own spiral neighbourhood, while other portions come from far more distant regions compressed into the same narrow strip. Dust complicates the picture by acting like a selective curtain, transparent in some directions, opaque in others, and never uniform. In visible light, the galactic centre is dramatic yet partially hidden, like a spotlight behind smoke. In infrared, much of that dust becomes less dominant, and the same region begins to reveal its crowded structure. Season and latitude decide what you can see and what you miss, because Earth's orbit changes which direction night faces. In the northern hemisphere, the summer sky often reveals the richest Milky Way star clouds, especially through constellations like Cygnus and Sagittarius. In the southern hemisphere, the galactic centre climbs higher and looks more dramatic, with the densest star fields rising into darker air. Near the equator, the band can arch overhead for long stretches of the year, forming a luminous bridge from horizon to horizon. Near the poles, it stays low, and the brightest regions may skim the horizon, where atmosphere dims and reddens them. The sky's brightest Milky Way features are real, but they're also a map of our viewing angle, an accidental projection of our place in the disk. For most of human history, that glowing river carried stories, not measurements, because the sky was a canvas for meaning. Cultures described it as milk, smoke, a road, a serpent, a bridge for souls, or a seam in the heavens where worlds touch. The band looked like a boundary of the cosmos, not a structure within it, because nothing in daily life suggested a larger container. Early philosophers argued about its nature, debating whether it was a burn mark, an atmospheric phenomenon, or a distant concentration of stars. The eye alone could not resolve it, and without resolution, there was no reliable way to separate structure from metaphor. The first crucial shift came with the telescope, when starlight began to separate into countless points, and the mist became a crowd. In the 17th century, observers proposed that the Milky Way was made of many faint stars, and telescopic views supported the claim. That idea was correct, but it did not yet reveal the galaxy's shape because a pile of stars can still hide its geometry. In the 18th century, star count suggested a flattened system, and thinkers tried to infer the sun's position by comparing densities in different directions. Dust made the counts misleading, because it thins the apparent star field and mimics an edge where none exists. In the 19th century, photography and spectroscopy added new tools, capturing faint stars and splitting light into chemical signatures. Yet the scale remained uncertain, and the Milky Way still felt like the universe itself because nothing larger was proven beyond doubt. Then came the tension that defined modern astronomy. Are the spiral nebulae nearby clouds inside our galaxy, or distant galaxies of their own? This was the island universe debate, and it was really a debate about distance, not about aesthetics. If the nebulae were close, the Milky Way was the main stage, and spiral structure was a local weather pattern. If they were far, the Milky Way was one actor in a much larger cast, and the night sky was a census of other systems. The answer required a reliable yardstick, not a better myth, because arguments collapse when the scale is unknown. What looks small can be enormous, and what looks nearby can be unimaginably far. In the 1920s, variable stars in the Andromeda Nebula provided that yardstick, and the logic was elegantly physical. Their brightness changes revealed their true luminosity through a period, luminosity relationship, and therefore their distance through simple inverse square dimming. Andromeda was far beyond the Milky Way, so it had to be another galaxy, not a local cloud. The Milky Way shrank from being the universe to being a single example, and that shift redefined our cosmic address. That demotion was also an invitation, because now our galaxy could be compared, classified and measured against others, rather than treated as the whole. To begin any later fact, we need scale anchors that hold the story steady, because intuition fails at tens of thousands of light years. The Milky Way's stellar disk spans roughly 100,000 light years or more across, depending on how you define its edge and which traces you use. If you imagine light crossing that diameter, it travels for 100 millennia before it reaches the other side, and it still remains inside the galaxy's gravitational reach. The thin disk, where many young stars and gas clouds live, is about 1,000 light-years thick, a flattened layer compared with its width. A thicker disk component extends farther above and below the plane, with older stars and different chemistry that hints at earlier, rougher epochs. These numbers are large, but they are still finite, and they set the boundaries of our home system in a way myths never could. We also need to place the Sun on that map, because our location biases everything we observe and everything we infer. The Sun sits in the disk, not at the centre, and not near the edge, which means our view is neither panoramic nor symmetrical. It lies about 26,000 light-years from the galactic centre, in a minor spiral feature called the Orion Arm or local spur. That placement matters because spiral arms are not rigid spokes, but regions where gas and stars bunch up and drift through. From here, we look inward through crowded regions and outward into thinner territory, and the difference is visible even to the naked eye. Our viewpoint is like living in a suburb and trying to infer the city's downtown shape through haze. Streetlights glare, distant towers overlap, and the skyline changes with every step. The Milky Way is not just a shape in space, it is a history in time, written into star ages, orbital patterns, and chemical fingerprints that act like forensic evidence. The galaxy began assembling more than 13 billion years ago, soon after the first stars could form and the earliest heavy elements were forged. It grew through mergers, gas inflow, and ongoing star formation in the disk, and those processes left scars in the halo and thick disk. The Sun is much younger, about 4.6 billion years old, born from enriched gas after many stellar generations had lived and died. That age difference matters, because the Sun carries a late chapter of the galaxy's chemical story: carbon, oxygen, silicon, iron, and the other ingredients of rocky worlds. Chemical enrichment is slow but relentless, and it makes the galaxy's past measurable in the present. The earliest stars formed from nearly pristine hydrogen and helium, so they contain very little of what astronomers call metals, meaning elements heavier than helium. Later generations formed after supernovae and stellar winds seeded the gas with heavier atoms, so their spectra record a richer mixture. In plain terms, starlight carries a barcode, and the barcode tells you what earlier stars contributed. When we map those barcodes across the disk and halo, we are mapping time as well as space. Time inside a galaxy is also measured by motion, and motion is the galaxy's most honest language. The Sun orbits the galactic centre, pulled by the combined mass of stars, gas, and dark matter, and the orbit is not a perfect circle. One full orbit is called a galactic year, and it takes roughly 225 to 250 million Earth years, depending on the Sun's exact speed and distance. That means the Sun has completed only about 20 orbits since it formed, which is a surprisingly small number for something that feels ancient. The number is unsettling, because it makes the galaxy feel less like a static backdrop, and more like a rotating machine with moving parts. Motion complicates observation, because we never stand still, and every measurement is taken from a moving platform. The Earth spins, the solar system moves, and the Sun circles the centre, so the sky is a shifting geometry rather than a fixed dome. Stars have their own velocities, and gas clouds stream along spiral structure, sometimes forming new stars where conditions compress and cool. Dust blocks visible light, especially toward the centre, so our most dramatic direction is also our most obscured. Perspective compresses distant features into the same thin band, blending separate regions into a single apparent ribbon. Every map we draw must correct for these biases, or it will be a beautiful mistake that feels true. So how do we measure distances when the scene is crowded and dim, and when the ruler itself is moving? The first rung is parallax, the apparent shift of a nearby star against distant background as Earth orbits the Sun. Parallax is geometry, and it is the cleanest distance method when it can be measured, because it depends on angles rather than assumptions about brightness. The shift is tiny, often smaller than a pixel in a typical image, so precision instruments are required. The Gaia spacecraft has turned parallax into an industrial survey, charting positions and motions for over 1 billion stars with extraordinary accuracy. Gaia does not reach every corner, but it builds the local framework that other methods must match, and it reveals streams and clusters as coherent motion patterns. Beyond parallax, astronomers use standard candles, objects with known intrinsic brightness, which turns light into a distance estimate. Cepheid variables pulse with periods that reveal their true luminosity, because the physics of their expanding and contracting atmospheres links period and energy output. Arlery variables do something similar for older stellar populations, especially in globular clusters in the halo, where Cepheids are rarer. Compare true brightness to observed brightness, and distance follows. If dust extinction is corrected with care, that correction is not cosmetic, it can change the inferred distance by thousands of light years in dusty directions. Standard candles extend the distance ladder deeper into the galaxy and outward to other galaxies, connecting our local measurements to the wider universe. Another tool is main sequence fitting, which uses the predictable relationship between a star's colour and luminosity, a consequence of stellar mass and temperature. In a star cluster, many stars share an age and distance, so their sequence can be compared to calibrated sequences nearby that have known distances. Shift the sequence until it matches, and you infer the cluster's distance, like aligning two transparencies until the patterns overlap. This method depends on good calibration, good dust corrections, and careful population assumptions, because metallicity and age can subtly move the sequence. It is powerful, but it reminds us that distance is never just one number, and certainty is never free. Distance is the hardest first step because everything else depends on it, and errors propagate like cracks in a foundation. Mass estimates rely on orbital speeds at known radii, and the radii are distances converted into physical scale. Luminosities become energies only when distances are secure, because brightness alone does not tell you power. The size of the bar, the pitch of spiral arms, and the thickness of the disk all change with the yardstick, sometimes enough to rewrite a model. Even the island universe debate was at its core a fight over scale, because scale decides what kind of object you are seeing. When distance is wrong, the galaxy's blueprint becomes a distorted projection, and the distortion can look convincing. As measurements improved, the Milky Way became a defined object with components and boundaries, each with a role in the larger system. The disk is where most of the gas and young stars concentrate, and where spiral structure is traced by star-forming regions and glowing nebulae. The bulge is a central swelling of stars, thicker and older on average than the thin disk, and dynamically more complex. The bar is an elongated stellar structure crossing the centre, influencing orbits and funneling gas inward, which can feed bursts of star formation. The halo is a diffuse realm of old stars and clusters, extending far beyond the bright disk and preserving evidence of past mergers. Each word is a clue to formation, because each component preserves a different era, like layers in rock that record changing conditions. Yet we still cannot take the one photograph that would settle every argument, because we cannot fly outside the disk for a clean overhead view. We infer the spiral pattern from star counts, gas maps, and motion, and we test those inferences against simulations of how disks behave. We infer the bar from infrared surveys that see through dust better than visible light, revealing asymmetries and elongated density patterns. We infer the dark matter halo from how fast objects orbit at large distances, where visible matter alone cannot explain the speed. Our galaxy is both familiar and hidden, because we are embedded in its plane, and the plane is where the obscuring dust lives. The Milky Way is the nearest great unknown, and that is why it matters, because it is the only galaxy we can study star by star at enormous scale. This documentary is built as a guided descent from wonder into precision, without losing the wonder along the way. We start with what the eye sees, then we add geometry, physics, and statistics, and we watch the glow become a measurable structure. We will count facts, but the goal is not trivia, and it is not a list of disconnected numbers. The goal is to understand how knowledge is extracted from biased viewpoints and incomplete data, and how uncertainty is reduced rather than erased. Each fact is a rung on a ladder that climbs from the backyard sky to the galaxy's edge, and each rung is tested by multiple methods. Now we need a blueprint because a system becomes knowable when its parts are mapped. Next, we move from the band of light to the architecture that makes it, and we keep asking what the light is hiding. We follow the disk into its arms, trace the bar through the dust, and weigh the halo we cannot see, using motion as our scale. The Milky Way will stop being a glow overhead and become a structure with addressable places, where here and there have meaning. Now we need a blueprint because a system becomes knowable when its parts are mapped. From inside the disk, the Milky Way refuses to hold still as a simple picture, because every direction is a stack of overlapping structures. Every line of sight layers different distances, different ages, and different kinds of light, like looking through a crowded city from street level. Dust erases the center in visible wavelengths, so the most important region is also the hardest to read. Even when we think we see a boundary, we may be seeing a veil, not an edge. There's also a psychological trap in galactic mapping, and it is surprisingly hard to escape. When we look at other spirals, we see clean arms and a bright core, and our brains want the same clarity here. But we're embedded in the very material we're trying to chart, and that turns geometry into inference. A nearby cloud can blot out a distant cluster, and a bright young association can masquerade as a major structural feature. The Milky Way becomes a puzzle where the missing pieces are not empty space, but hidden space. Start with the disk, because the disk is the galaxy's main habitat for stars and gas. Visually, imagine a luminous, rotating plate, thin enough to seem delicate from afar, yet wide enough to hold most of the galaxy's star formation. The disk is not one layer, but at least two overlapping stellar populations, interleaved like transparent sheets. The thin disk is flatter, colder in its motions, and richer in gas, which makes it the galaxy's most active nursery. It hosts most ongoing star formation, open clusters, and many of the brightest blue stars that dominate short exposures. The thick disk is puffier, older on average, and poorer in heavy elements, so its light is subtler and redder. Its stars move with higher random velocities, so their orbits look dynamically hotter and less neatly circular. That orbital temperature is not heat, but the amount of disorder in motion. In plain terms, it measures how much a star's path jitters away from a smooth circular track. A dynamically cold population stays close to the midplane and keeps a relatively orderly rotation, like cars flowing along a broad highway. A dynamically hot population bounces higher above the plane and wanders more in radius as it orbits, as if the lanes themselves were shifting. Those differences matter because gravity remembers motion, and motion remembers history. The disk's thickness is also an observable geometry, not just a metaphor. The thin disk has a smaller scale height, meaning its star density drops quickly with altitude above the plane. The thick disk declines more slowly, so it becomes more important when you look toward higher galactic latitudes. In images, this is subtle, but in star counts, it is unmistakable. Two overlapping exponentials that imply two different dynamical states. Age, chemistry, and motion link the two disks to different chapters of history. Thin disk stars tend to be younger and more metal-rich, reflecting longer chemical recycling through generations of stellar birth and death. Thick disk stars tend to be older and more metal-poor, reflecting earlier enrichment when fewer supernovae had seeded the gas. Metallicity here is a kind of timestamp, an imperfect one, but still a clue. Their vertical excursions above the plane preserve evidence of past heating events, whether from mergers, internal instabilities, or long-term scattering. The boundary between thin and thick is not sharp, and surveys still debate how many subcomponents exist. Some stars sit in the overlap, carrying mixed signals like bilingual witnesses. Chemistry adds another layer of meaning, because not all elements are made on the same schedule. Alpha elements such as oxygen, magnesium, and silicon are produced efficiently in core collapse supernovae, which happen quickly after massive stars form. Iron builds up more slowly, because a significant fraction arrives through Type Ia supernovae on longer delay times. That means a star's ratio of alpha elements to iron can hint at how rapidly its birth environment was enriched. When astronomers talk about chemical tagging, they are chasing the idea that shared abundance patterns can reveal shared origins. an ambition that becomes harder as mixing and migration blur the record. Even the best tags can smear, because the disk is not a sealed laboratory, and it never was. The disk is also a working ecosystem, where gas cycles through clouds and stars. Cold molecular clouds collapse into clusters, then feedback reshapes the surrounding medium, carving cavities and compressing nearby regions. Supernovae and winds stir turbulence and seed new heavy elements into gas, which later becomes the raw material for new stars and planets. Ultraviolet radiation can photodissociate molecules at cloud surfaces, while dense interiors remain shielded and cold. Over time, stars drift from their birthplaces, so today's neighbourhood is a mixed archive rather than a single family. Some drift happens gradually through interactions with spiral structure and giant molecular clouds. Some happens abruptly when clusters dissolve and their members disperse into the field. The disk therefore records both formation and migration, which complicates any clean map. A star's current position is not necessarily its birthplace, and that breaks the simplest attempt at galactic archaeology. If you could paint the disk by age, you would not see neat rings, but mottled swirls and scattered patches. If you could paint it by metallicity, you would see gradients, but also local exceptions that hint at radial mixing. The disk is a library where the books have been reshelved many times. The question is not whether the record exists, but how much of it remains legible. Spiral arms are the next piece of the blueprint, and they are easy to misunderstand. Arms look like solid structures, but they are not rigid spokes made of the same stars, fixed in place like the blades of a fan. Their visual sharpness comes from contrast, not permanence. In one picture, arms are density waves, long-lived patterns that rotate with their own speed through the disk. Gas enters the wave, compresses, forms stars, then exits as the pattern continues, leaving a trail of luminous, short-lived markers. In another picture, arms are transient features that grow, shear, and fade under gravity, then reappear elsewhere as the disk responds. Many models now suggest a mix, with segments that persist while details change from orbit to orbit. Either way, arms are patterns in density, not permanent material objects. The stars you see in an arm today will not necessarily remain in that arm forever, because they orbit the centre on their own schedules. Differential rotation stretches features, because inner orbits move faster than outer ones, and that shear is relentless. That shear is why spiral patterns are so hard to keep coherent without some organising mechanism. The result is a galaxy that looks like a pinwheel, but behaves like a rotating flow, with traffic patterns rather than fixed roads. It helps to imagine time-lapse photography, and to imagine it honestly, at the scale of millions of years per second. Over tens of millions of years, clouds slide into a denser region, brighten with newborn stars, and then drift onward as the most massive stars explode. The arm is not the same material, but the same recurring compression. What we call an arm is partly a definition imposed by our eyes, because our eyes are drawn to bright, young, high-contrast features. The older stellar disk underneath can be smoother than the arm traces suggest, like a steady glow beneath flashing lights. Arms announce themselves because star formation lights them up. Massive young stars burn bright and die quickly, so they trace recent birth sites with almost no memory beyond a few million years. H2 regions glow where ultraviolet radiation ionizes surrounding hydrogen, producing emission lines that stand out even at great distances. Dust lanes and molecular clouds mark where gas is densest and most ready to collapse, often appearing as dark cuts in optical images of other galaxies. When we see a bright arm segment in another galaxy, we are often seeing the short-lived highlights. The underlying older stellar disk can be smoother than the arm traces suggest, and that mismatch is part of the mapping challenge. From our position, the arm pattern becomes a puzzle of overlapping tangents. We do not hover above the galaxy with a camera, so we infer structure by looking along the plane and noticing where traces pile up. Some directions cut across an arm, while others skim along it, producing bright tangent points that can trick us into thinking a segment is longer or stronger. We sit in the local spur, also called the Orion arm segment, between larger arms. It is not always treated as a major arm, but it is real in gas and young stars, and it is close enough to dominate our sky. It contains nearby star-forming regions that shape familiar constellations, from glowing nebulae to dark rifts. It also biases our sense of what an arm looks like, because we live inside one. Nearby star-forming complexes loom large, while distant ones fade behind dust and distance. If you could step outside the galaxy and look back, the local spur might appear as a modest bridge or branch, not a grand sweeping arm. Yet from within it, it feels like a defining feature of the local cosmos. That is a recurring theme in this blueprint. Our viewpoint magnifies the nearby and diminishes the far. The major arms are usually named Perseus, Sagittarius Carina, and Scutum Centaurus. Some maps add the Norma arm or treat it as part of a larger structure, depending on how continuity is judged. The exact number of arms, their pitch angles, and their continuity remain debated, and the debate is not just semantics. Part of the disagreement comes from using different traces that respond to different physics. Gas, dust, young stars, and old stars do not always line up in the same way, because they peak at different phases of the star formation cycle. In some models, the gas shock sits slightly offset from the stellar density maximum, and that offset can shift an arm's apparent location. Distance errors amplify that uncertainty, because a small mistake shifts an arm across the map. Kinematic distances rely on assumed rotation, which can fail near the centre where orbits are strongly influenced by the bar. Streaming motions near arms can mimic distance shifts, because gas is not on perfect circular orbits and can move inward or outward as it passes through patterns. In the inner galaxy, multiple distances can match the same observed velocity, creating a near-far ambiguity that must be broken with additional clues. In the outer galaxy, signals weaken and warp complicates the geometry, so features can be misassigned to the wrong radius. The blueprint is therefore a probabilistic sketch, not a final diagram etched in ink. Dust is the great obscurer that forces us into indirect methods. In visible light, extinction rises sharply toward the galactic centre and along the plane, turning what should be a bright hub into a dim, mottled band. Dust grains scatter and absorb, reddening starlight and hiding distant populations, and the effect depends on wavelength. Shorter wavelengths are punished more severely, so blue light disappears first and red survives longer. Star counts in optical bands can falsely suggest edges and gaps where dust is simply thicker, like fog banks hiding buildings. This is why early maps underestimated the galaxy's size and misplaced the Sun, because the visible universe seems smaller than it is. Historically, this was a hard lesson, and it arrived in stages rather than as one clean correction. Early 20th century astronomers argued over whether the Milky Way was the whole universe, or one galaxy among many. Dust was an uninvited participant in that debate, because it dimmed distant stars and made the system look compact. As understanding of interstellar extinction grew, the scale of the galaxy expanded, and the Sun's apparent centrality dissolved. The fix is not one instrument, but many windows across the spectrum, each compensating for the other's blind spots. Infrared light penetrates dust better, so it reveals crowded fields behind the curtain. Near-infrared surveys map the distribution of older stars and the central bulge more reliably, because those stars emit strongly at longer wavelengths. Mid-infrared highlights warm dust and star-forming regions that are invisible in optical, revealing filaments and bubbles carved by feedback. Radio waves pass through dust almost unhindered, so they trace gas across the disk, even on the far side of the galaxy. X-rays and gamma rays reveal high-energy sources and hot plasma, but they sample a different side of the ecosystem, where gravity and magnetic fields accelerate particles. Each band shows a different Milky Way, and the blueprint must combine them into a coherent, if imperfect, whole. A useful way to picture this is as a layered composite. In optical, the Milky Way is a bright river cut by dark lanes, with the centre strangely muted. In infrared, the river thickens into a dense glow, and the central region becomes crowded with stars. In radio, the disk becomes a web of gas, with arcs and shells that hint at past explosions. The same galaxy, but different truths depending on how you look, so the blueprint must be multi-wavelength by design. Radio mapping begins with hydrogen, because hydrogen is everywhere and it speaks at 21 centimeters. The 21 centimeter line comes from a spin-flip transition in neutral hydrogen, when the electron and proton change their relative orientation. It is weak per atom, but the galaxy contains so much hydrogen that the signal is strong when integrated across vast clouds. By measuring Doppler shifts, astronomers infer line-of-sight velocities of gas, turning frequency into motion. With a rotation model, those velocities become approximate distances and a spiral structure map. This method built the first large-scale arm sketches, even before precise stellar distances were common. The elegance of the 21 centimeter line is that it is both a tracer and a ruler of sorts. It reveals where neutral gas resides, and it also reveals how that gas moves in the galactic potential. Yet it carries assumptions, because converting velocity to distance requires a model of rotation and an assumption about circular motion. Where the bar and arms disturb the flow, the conversion becomes less trustworthy. Even the line profile can hide complexity, because multiple clouds at different distances can share similar velocities. That is why the map built from hydrogen is powerful, but never final. Molecular gas is mapped with carbon monoxide, because cold H2 is hard to observe directly. Molecular hydrogen has no strong dipole emission at the low temperatures of typical clouds, so it hides unless we use proxies. CO emits at millimetre wavelengths that radio telescopes can survey efficiently, and its lines can be bright even in cold environments. CO clouds trace the densest star-forming reservoirs, which often concentrate along arms and in the inner galaxy. Comparing CO maps with 21 cm maps separates cold molecular regions from more diffuse atomic gas. It also shows that arms are not uniform, but clumpy and segmented, with giant molecular complexes spaced like beads. The star formation pattern becomes a chain of complexes rather than a continuous ribbon. In some regions, you see a sequence: dense molecular gas, then embedded infrared sources, then exposed H2 regions, then supernova remnants and expanding shells. That sequence is not always clean, but it hints at a life cycle. It also reminds us that an arm is not just a line on a map, but a conveyor of phases: cold gas, collapsing cores, luminous stars, and recycled debris. If the arm is a pattern, then these phases are the moving ink that briefly makes it visible. For precision, mesas provide a geometric anchor inside the spiral pattern. Mesas are natural microwave lasers produced in dense regions near young massive stars, often in shocked gas where conditions align just right. They create extremely bright, compact radio points that can be measured with very long baseline interferometry, using antennas separated by continents. VLBI can measure parallax and proper motion for masers across the galaxy, achieving distance accuracy that feels almost impossible at such scales. Those distances do not depend on a rotation model, so they calibrate the arm map directly. Maser results have revised arm positions and revealed strong non-circular motions, showing that gas responds to more than simple rotation. There is something philosophically striking about this technique. The galaxy is vast, yet tiny maser spots, pinpricks of coherent emission, become the nails that pin down the blueprint. With repeated observations over Earth's orbit, the apparent shift of a maser against distant background sources yields parallax, and parallax yields distance. It is geometry in its purest form, and it turns the Milky Way from an inferred outline into a measured structure. In a sense, we are using Earth's motion as part of the instrument, letting the planet's orbit draw a baseline across space. With these tools, the map starts to show a central bar rather than a simple round bulge. In visible light, the center is blocked, so the bar was inferred late and argued over, especially because our viewpoint makes symmetry hard to judge. Infrared surveys revealed an elongated distribution of stars across the inner few kiloparsecs, like a luminous spindle embedded in the disk. Star counts show asymmetry, with one side appearing closer and brighter, consistent with a tilted bar. Stellar motions also indicate elongated orbits consistent with a bar potential, as if stars are streaming along an oval track. The Milky Way is therefore classified as a barred spiral, but the bar's exact length and angle remain active topics. The bar matters because it reshapes the flow of gas. Bars exert torques that remove angular momentum from gas in the inner disk, and without angular momentum, gas can fall inward. Gas can then spiral inward along bar-driven lanes, piling up near resonances where orbital frequencies align in special ways. That inflow can feed central star formation and build dense rings, which can appear as bright infrared structures. It can also help supply the central molecular zone, one of the galaxy's richest gas reservoirs, dense and turbulent. In other galaxies, bars correlate with nuclear starbursts, and the Milky Way shows hints of similar processes, though on a more moderate scale. Visually, you can imagine dust lanes along the leading edges of the bar, like dark seams where gas is shocked and compressed. In infrared and radio, those seams become bright ridges and filaments, tracing inflow toward the center. The bar is not just a shape, but a machine part, an engine of redistribution that can rearrange gas over hundreds of millions of years. It raises a question that lingers in the background. how much of the galaxy's present-day structure is an internal product, and how much was imposed by external encounters? The bulge is not just a spherical swelling, and its shape carries dynamical history. Many lines of evidence support a boxy or peanut-shaped bulge, visible in infrared star counts and supported by stellar kinematics. Such bulges often form when a bar buckles vertically and thickens, a kind of instability that lifts stars above and below the plane. That implies the bulge is partly a product of disk evolution, not only an ancient merger remnant. The bulge contains old stars, but it also contains multiple populations with different metallicities, implying a complex formation timeline. Its structure suggests that secular evolution and early formation both contributed, layered rather than exclusive. The boxy bulge also changes how we interpret the center's symmetry. A peanut shape means the density is not the same in all directions, and that affects how we count stars through dusty windows. It affects microlensing rates, because more mass along the line of sight increases the chance of gravitational lensing events. It also affects inferred mass distributions, because assumptions of spherical symmetry can mislead. The question of whether there is a small classical bulge component remains open, and the answer matters for the galaxy's early history. Some models allow a modest classical bulge embedded within the boxy structure, like an older core wrapped in a younger dynamical shell. The blueprint therefore includes nested components, each with different origins. In the inner few kiloparsecs, disk, bar and bulge are not separate boxes but overlapping dynamical families. Stars can be trapped on bar-supporting orbits, then scattered into thicker configurations by buckling. Gas can flow inward, form stars, and add younger populations to an older background. The center becomes a palimpsest, written and rewritten by gravity. When we look toward it, we are not seeing one event but the superposition of many. Beyond the bright inner regions, the disk itself bends and thickens. The outer disk is warped, meaning the midplane tilts upward on one side and downward on the other, like a vinyl record left too close to heat. The warp is seen in neutral hydrogen maps and in stellar tracers, and it becomes more pronounced at large radii. The disk also flares, meaning its thickness increases with radius as the gravitational restoring force weakens. Flaring suggests weaker restoring gravity in the outskirts, and stronger perturbations over time, including the cumulative effect of passing satellites. The galaxy's edge is therefore not a clean circle, but a twisted, thickened sheet that fades into the halo. The causes of warp and flare are still debated, and each candidate points to interaction. Satellite galaxies can tug on the disk through repeated passages, raising bending waves that travel through the stellar and gas layers. A misaligned dark matter halo can torque the disk over long timescales, slowly twisting the outer regions. Accretion of intergalactic gas can arrive with angular momentum tilted relative to the disk, forcing the outskirts to compromise. The warp may also be a superposition of bending waves that travel through the disk and interfere. Whatever the cause, the warp is evidence that the Milky Way is not isolated, even if it looks serene to the naked eye. All of this structure is shaped by rotation, so the blueprint must include the rotation curve. The rotation curve describes orbital speed as a function of distance from the center, turning the galaxy into a measurable dynamical system. If mass followed light alone, speeds would fall with radius like planets around the Sun, because gravity would weaken as visible mass thinned out. Instead, observed speeds stay high, far into the outer disk, remaining roughly flat across large ranges. Gas and stars orbit faster than visible matter can easily explain, and that mismatch is one of astronomy's most persistent clues. It is not a small discrepancy, but a structural demand for additional gravity. Rotation measurements come from multiple tracers, each with its own biases. Neutral hydrogen provides velocities across huge radii, but distances can be uncertain, and non-circular motions can contaminate interpretations. Stellar motions from surveys like Gaia provide local precision, including proper motions and parallaxes for vast numbers of stars, but require modelling to extend globally. Masers give accurate distances and proper motions for specific regions, but they sample star-forming sites rather than the whole disk. Combining these data yields a rotation curve that is broadly flat over large ranges, with details that depend on assumptions about the Sun's motion and the galaxy's parameters. The implication is not yet a solved mystery, but a pressure point in the narrative. Unseen mass enters the blueprint as a gravitational scaffold rather than a visible component. We do not resolve the dark matter question here, but we set the stakes because the rotation curve is a dynamical statement. The disk, arms, bar, and bulge move within a larger potential that shapes their orbits, even when we cannot see the source directly. The rotation curve is the simplest clue, but not the only one, and it is supported by other dynamical hints. Vertical motions, warp dynamics, and satellite orbits also respond to the hidden mass, as if the visible galaxy is embedded in a larger invisible shape. The blueprint therefore includes a contour we cannot directly photograph, but we can feel it through motion. Even the visible blueprint resists simplification, because each tracer draws a different outline. Young stars trace arms sharply, but they ignore older populations between arms, which carry much of the mass. Gas traces shocks and flows, but it responds to pressure, magnetic fields, and feedback as well as gravity. Infrared star counts trace mass better, but crowding and extinction still matter near the center, and selection effects can bias what we count. Kinematic models assume rotation, but bars and spiral streaming break those assumptions, especially inside the solar circle. The more we measure, the more the Milky Way looks like a living pattern, not a static diagram. This is the suspense at the heart of mapping our own galaxy. We can outline a barred spiral with multiple arms and a warped disk, and we can place the Sun within it with increasing confidence. Yet the exact arm layout shifts as new distances arrive, and new models compete, sometimes moving a feature by kiloparsecs. The bar's angle and length adjust as surveys improve, and selection effects are corrected, and even small changes alter resonance locations. The bulge's populations complicate any single formation story, because chemistry and kinematics refuse to align into one neat narrative. The outer disk's warp reminds us that the blueprint is being rewritten by interaction, not preserved in isolation. So the Milky Way is not a static pinwheel, but a rotating system of coupled parts. The thin disk forms stars and highlights arms, while the thick disk preserves older, hotter orbits that carry memory of earlier conditions. Spiral structure organizes gas without permanently trapping the same stars, creating patterns that persist even as participants change. The bar funnels material inward and can reshape the bulge through buckling, turning internal dynamics into visible architecture. The disk bends and flares, responding to forces beyond the bright starlight, including satellites and the larger gravitational environment. Dust forces us to stitch the map from infrared, radio, and high-energy windows, because no single wavelength tells the whole truth. With scale and distance in hand, we can begin mapping the Milky Way's disk, arms, bar, bulge, and halo. But mapping is not the end, because structure is made by motion and maintained by forces, and those forces leave signatures in speed and flow. The blueprint is a snapshot of a process, not a finished plan, and the process continues as we speak. Next, we follow rotation through the disk, track magnetic fields in the gas, and confront the invisible mass implied by the galaxy's speed. The blueprint becomes a machine diagram, and the machine is still running. The Milky Way blueprint only matters if it moves, because motion reveals hidden mass that light alone can conceal. From inside the disk, we cannot step back for a clean photograph, so we rely on dynamics, measuring how stars and gas respond to gravity. In practice, that means turning the sky into a laboratory, where velocities become clues and orbits become equations written in starlight. Start with the Sun, because our measurements ride on its orbit like instruments bolted to a moving ship. The Sun circles the galactic center at about 220 kilometers per second, a speed that would cross Earth in minutes. That number is not just trivia, because it anchors the local standard of rest used in many surveys. When astronomers correct a star's measured velocity, they often subtract the Sun's motion first, otherwise our own drift contaminates the map. One full circuit takes roughly 225 to 250 million years, which astronomers call a galactic year. The range reflects uncertainties in distance and rotation speed, and it reminds us that even our best constants are measured, not assumed. Those uncertainties are not embarrassing. They are the honest edges of a measurement made from within the system. That means the Sun has completed only about 20 galactic years since it formed, a surprisingly small count for something that feels ancient. To be in orbit is to be continuously falling, guided by a gravitational field we infer rather than directly see. The center is not a bright beacon in visible light, because dust in the disk absorbs and scatters starlight. In optical images, the inner galaxy looks like a dimmed lantern behind smoke, with dark lanes cutting across the glow. Those lanes are not empty space, but cold grains and gas that block the view like soot on glass. Yet the orbit is real, because the sun's speed and direction are measurable against other stars through Doppler shifts and proper motions. Doppler shifts tell us how fast something moves toward or away from us, while proper motion tracks its drift across the sky. Combine those with distance estimates, and a three-dimensional velocity emerges, quietly precise, even when the object is thousands of light-years away. We define a galactic center by the symmetry of motions, not by a single visible landmark, and that is a subtle but powerful idea. Historically, that idea took time to earn trust, because early astronomy was built on what the eye could see. In the early 20th century, debates about the Milky Way's size and the Sun's location were still unsettled. Harlow Shapley used globular clusters to argue for a distant centre, while others questioned whether dust was skewing the picture. As radio astronomy matured, the galaxy's hidden structure began to emerge, especially through hydrogen mapping and later infrared surveys. The lesson was humbling. The galaxy's true centre can be identified even when it is visually masked. Motion, not brightness, becomes the compass. The orbit is not a perfect circle, and it is not isolated from the disk's traffic. The Sun oscillates above and below the midplane, crossing the disk on long timescales that span tens of millions of years. That vertical motion is like a slow bobbing through a crowded sea of gas and stars, where density and radiation fields change with height. Even the night sky's background changes subtly with that motion, because dust and gas are not evenly layered. It also drifts in radius over billions of years, because spiral patterns and clouds exchange angular momentum with passing stars. This process, often called radial migration, can move stars far from their birthplaces without violently heating their orbits. The mechanism is gentle but relentless, like a series of small tugs that add up to a new address. Even our local neighbourhood is not a fixed address, but a path through changing environments that can influence comet clouds, radiation exposure, and the density of nearby gas. Rotation is the galaxy's main engine, but it is not rigid like a wheel bolted to an axle. The Milky Way shows differential rotation, meaning inner regions orbit faster than outer ones at different angular rates. This is not a detail, because it controls how patterns survive in a shearing disk and how gas is stirred. If the disk rotated like a solid plate, spiral features could remain locked in place, and the galaxy would look more like a spinning coin. Instead, the inner galaxy laps the outer galaxy, and time itself becomes a sculpting tool. Differential rotation stretches and twists any feature that tries to stay coherent, especially in the gas. Gas clouds and stellar groups are pulled into elongated shapes by shear, as neighbouring rings slide past one another. Over time, shear can turn local structure into long filaments and arcs, the way taffy stretches under steady pulling. In wide-field surveys, those filaments can appear as faint curving lanes of dust or as chains of star-forming knots. The disk becomes a flow, where patterns persist but the material inside them changes, and that distinction matters. Spiral arms live inside this tension between gravity and shear, and their nature is still actively debated. Arms can be long-lived density patterns, or transient segments that grow and fade depending on the model and the tracer used. In the density wave picture, the arm is more like a traffic jam than a convoy. Cars enter, slow, and then leave. In more transient pictures, arms are recurrent features seeded by instabilities and amplified by self-gravity, then shredded by shear. In either case, differential rotation means the same stars do not stay in the same arm for their whole lives. Gas enters a denser region, compresses, forms stars, and then drifts onward, leaving the luminous newborns as a temporary highlight. If we could watch in time-lapse, we would see bright blue clusters flare along an arm's edge, then fade as they disperse into the broader disk. The arm would remain recognizable, but its cast would keep changing, an illusion of permanence built from constant turnover. This matters for star formation, because compression competes with disruption in a constantly moving medium. Shear can tear clouds apart before they collapse, especially in regions with strong velocity gradients and strong tidal forces. In other places, compression wins, and giant molecular clouds form and fragment into clumps and cores. The result is a patchwork of star-forming regions that trace where the flow briefly favours collapse, often along arm segments or near resonances. When we look across the disk in infrared and radio maps, we see that patchwork as bright knots embedded in darker lanes of dust. The bar adds another layer to the story, because it drives non-circular motions in the inner galaxy. A bar is not simply a shape, but a rotating gravitational perturbation that can trap stars in elongated orbits. In near-infrared views, the bar's presence is suggested by a subtle, stretched brightness, like a spindle embedded in the bulge. Gas responding to the bar can shock along dust lanes, lose angular momentum and flow inward, feeding central reservoirs. Those flows complicate simple rotation models because velocities are no longer purely circular. Even so, the same principle holds. The pattern influences the flow, and the flow reveals the mass. We measure rotation with Doppler shifts and proper motions, then we turn those into a rotation curve. A rotation curve is speed versus distance from the centre, and it is a direct test of gravity. In the Milky Way, we infer it using multiple tracers: neutral hydrogen, molecular gas, mesas in star-forming regions, and stellar kinematics. Mesas are especially valuable because their narrow radio lines can yield exquisitely precise velocities and distances. Each tracer has its own biases, because distances can be uncertain and motions can include streaming along arms. Gas can also respond to shocks and pressure gradients, so it does not always behave like a simple test particle. Yet when the pieces are assembled, a consistent picture emerges that is hard to dismiss. The curve is not merely a graph. It is the galaxy's gravitational signature, extracted from millions of moving parts. If mass followed light alone, speeds would decline with radius like planets around the Sun, where most mass sits at the centre. In that case, the outer disk would orbit more slowly, and the rotation curve would fall. Instead, in the Milky Way and many galaxies, speeds stay high far out, remaining roughly flat over large ranges. The outer disk does not behave like a sparse fringe around a heavy core, but like a system embedded in a much larger gravitational field. That flatness is one of the strongest clues that most mass is not luminous. Visually, the rotation curve is a simple plot, but it carries an unsettling message. The outer disk does not contain enough stars and gas to hold those speeds by itself, even after careful accounting. Something else supplies gravity, extending beyond the visible edge, and it does so smoothly enough to maintain stable orbits. We can argue about details, but the basic mismatch is robust across methods and across galaxies. It is one of the rare astronomical results that repeats wherever we look. The mass budget makes the imbalance explicit, and it forces us to separate what shines from what weighs. Add up the mass in stars, stellar remnants, and gas, and you get a minority share of the galaxy's total. The gas includes atomic hydrogen, molecular hydrogen, and helium, plus a small fraction of heavier elements. The stars include everything from bright main sequence stars to dim red dwarfs and compact remnants. Even after adding those hidden baryons, the total mass inferred from dynamics is much larger, often by a factor of several. The Milky Way behaves like a bright disk embedded in a heavier invisible structure, like a lantern suspended inside a much larger shadow. That metaphor is not just poetic, it captures how gravity can be dominated by something we do not see. The disk's light draws the eye, but the halo's mass sets the rules of motion. This is where dark matter enters, not as a guess, but as a gravitational requirement that follows from the equations. Dark matter is defined by its effects, not by direct light, and that definition is deliberately cautious. It does not emit or absorb enough electromagnetic radiation to be seen in ordinary surveys, so it does not light up our detectors. Yet it shapes orbits, stabilizes the disk against some instabilities, and binds the galaxy's outskirts where visible matter thins. In simulations, a massive halo also helps explain why disks can persist for billions of years without being torn apart. The concept has a history that mirrors the slow accumulation of evidence in science. In the 1930s, Fritz Zwicky inferred missing mass in galaxy clusters from their velocities, a result that sounded extreme at the time. Decades later, Vera Rubin and collaborators showed that flat rotation curves were common in spiral galaxies, not a rare oddity. Each step tightened the net, because independent measurements pointed to the same conclusion. By the time modern surveys arrived, the question had shifted from whether dark matter exists to how it is distributed. Rotation curves are the simplest evidence, but not the only one, and the Milky Way offers several complementary tests. Satellite galaxies orbit the Milky Way at large distances, and their motions require a deep potential well. The Magellanic Clouds and many smaller dwarfs move as if they are inside an extended halo that reaches far beyond the bright disk. Their tidal distortions, stretched stellar shapes and stripped gas also depend on the halo's mass distribution. Even the survival of some satellites over cosmic time implies a gravitational environment that is strong and extended. Stellar streams provide another line of evidence, and they are unusually precise because they preserve dynamical information. Streams form when a globular cluster or dwarf galaxy is pulled apart by tides during repeated passages. The debris stretches into long, thin ribbons that trace the orbit of the original system, sometimes wrapping around the sky. In deep images, a stream can look like a faint brushstroke, barely brighter than the background. In star catalogues, it appears as a coherent overdensity with a shared motion, like a signature written in the halo. Phase space means position plus velocity, and it is where the galaxy's memory hides when shapes have blurred. A disrupted cluster can spread across the sky, but still share a tight velocity pattern that marks a common origin. A disrupted dwarf can leave multiple wraps, like layered loops around the galaxy, because it has orbited more than once while dissolving. Streams let us read the gravitational field because their shapes, widths, and precession respond to the potential. When a stream bends, fans, or splits, it is often gravity doing the writing. The precision comes from the fact that streams are cold in a dynamical sense, meaning their internal velocity dispersion is small. Small dispersions make them sensitive to subtle perturbations, including the global shape of the halo. A stream does not just trace where mass is, but how that mass is arranged in 3 dimensions. That is why stream modelling has become a frontier, because it turns the halo into a testable geometry. It also forces humility, because small modelling assumptions can shift inferred halo parameters. Moving groups and stellar streams are related, but they are not identical, and the difference is diagnostic. Moving groups can be dissolved clusters that share age and chemistry, making them true siblings separated by time. They can also be resonant features shaped by the bar and spiral patterns, where stars of different origins are sorted into similar velocities. Some groups share chemistry and age, which supports a common birth site and a shared enrichment history. Others share motion without shared chemistry, which suggests dynamical sorting rather than family ties. The galaxy, in other words, can create false families through gravity alone. Gaia made this field explode because it measures motions for enormous numbers of stars with unprecedented uniformity. With proper motions and parallaxes, we can identify structures that were invisible in star counts, especially when dust hides the plane. We can see ripples, arches, and clumps in velocity space that hint at past disturbances and ongoing resonances. Some of those disturbances may come from satellite passages that shook the disk, leaving waves that still ring. The data feel almost geological, as if the disk preserves earthquake layers in velocity rather than rock. Streams also probe what we do not know about dark matter, and that is where the story becomes delicate. If the halo were perfectly smooth, streams would be smooth arcs, broadened mainly by internal dispersion and observational error. If the halo contains clumps, streams can show wiggles, gaps, and heating, because passing masses perturb stellar orbits. Those signatures could come from dark subhalos predicted by cosmological simulations, which would otherwise be nearly invisible. But they can also come from baryonic structures like giant molecular clouds, spiral arms, or the disk itself. The inference is powerful, but it demands careful accounting of ordinary matter before claiming exotic structure. So the inference is strong, but it is not unlimited, and the boundaries matter for honesty. We can conclude that an extended dark halo exists with high confidence because multiple tracers demand it. We can estimate its mass within certain radii, and we can bracket the total mass with satellite and stream data. We cannot yet conclude the particle nature from galactic dynamics alone, because different microphysical models can produce similar gravitational fields. Dynamics tells us what gravity is doing, not what the gravitating substance is made of. The halo itself comes in 2 parts, and the distinction matters for both visuals and interpretation. There is a stellar halo, sparse and ancient, made of old stars and globular clusters on plunging orbits. There is also a much larger dark matter halo, extending far beyond the stellar distribution into regions where few stars roam. The stellar halo is a tracer of assembly history, because its stars often arrive through mergers and accretion. The dark halo is the main gravitational container, setting the potential in which everything else moves. When we picture the stellar halo, the imagery shifts from a bright disk to a faint three-dimensional fog. Globular clusters hang like distant lanterns, each a dense swarm of old stars. Halo stars are metal-poor on average, meaning they formed when the universe had fewer heavy elements. Their orbits are often eccentric and tilted, suggesting they were not born in the thin disk's orderly rotation. In their chemistry and motion, they carry a record of the Milky Way's growth. The halo's shape is a live question, because shape changes orbits in ways that accumulate over billions of years. A spherical halo produces one family of stream paths and satellite precession rates, with symmetry that makes modelling simpler. A flattened or triaxial halo produces different precession, different stream fanning, and different orbital alignments. The Milky Way's halo may not be perfectly symmetric, and small asymmetries matter over cosmic time. If you follow an orbit long enough, even a slight distortion becomes a significant deflection. Triaxial means the halo has three unequal axes, like a stretched ellipsoid whose long and short directions do not match. That shape can arise naturally in simulations of structure formation, where dark matter collapses and merges along cosmic filaments. Baryonic physics can also reshape the inner halo, because the disk's gravity and feedback can pull the distribution toward rounder forms. Observations are still sorting out how the inner and outer halo differ, and whether the halo twists with radius. The answer is not merely geometric, because it affects how we interpret every stream and satellite orbit. And here's something that should stop you cold. For all our telescopes, all our physics, all our centuries of studying the sky, we still don't know how much our own galaxy weighs. Not off by a little, off by billions upon billions of suns. We can weigh galaxies across the universe, yet the one we live inside remains stubbornly out of focus. And later in this video, you'll see why the answer to this single question quietly controls the fate of the Milky Way itself. For now, look at why the scale won't settle. Even the total mass of the Milky Way remains uncertain at the tens of percent level, and that uncertainty has practical consequences. Different tracers sample different radii, and the halo's outer edge is not a sharp boundary but a gradual thinning. Some estimates emphasize satellite velocities, others emphasize escape speed near the Sun, others emphasize stream modelling. Each method has systematics, including anisotropic orbits and incomplete samples. The galaxy's weight is measurable, but not yet pinned to one final number, which is why new data keep reshuffling the range. Gravity is not the only force threading the disk, because the interstellar medium is not passive and not simple. The ISM is a multi-phase ocean of gas and dust with pressure, turbulence, and magnetic fields that act like unseen currents. It flows through the gravitational potential, but it also resists, cools, heats, and fractures as energy is injected. The galaxy's motion engine is therefore coupled to a complex fluid, not just to collisionless stars. When we say the disk rotates, we are compressing a whole meteorology into one phrase. The hot ionized medium is thin and energetic, often around 1,000,000 Kelvin, and it is associated with violent events. It fills large volumes in bubbles and cavities carved by supernovae and winds, creating superbubbles that can break out of the disk. Its density is extremely low, closer to a few particles per cubic centimetre or less, far thinner than any laboratory vacuum most people imagine. It is hard to see directly, but it glows in X-rays and leaves absorption signatures in the spectra of background sources. In all sky maps, it appears as a faint mottled halo of emission, hinting at a hot atmosphere around the galaxy. The warm neutral medium sits at more moderate temperatures, often thousands of Kelvin, and it forms much of the diffuse disk gas. It can be traced by the 21 centimetre line of hydrogen, a radio transition that became a cornerstone of galactic astronomy. That line arises from a subtle flip in hydrogen's electron-proton alignment, and its rarity is balanced by the sheer abundance of hydrogen. It allows us to map gas through dust, because radio waves pass where visible light fails. Its density is still low by everyday standards, but it carries much of the atomic gas mass that feeds future clouds. It acts as a reservoir that can cool into denser phases when conditions allow. Cold molecular clouds are the densest phase, often tens of Kelvin in their interiors, and they are the true star factories. Their densities can reach hundreds to millions of particles per cubic centimetre in cores, where gravity begins to win. This is where stars form because cold temperatures reduce pressure support and allow collapse to proceed. Molecular hydrogen dominates. but we often trace these clouds with carbon monoxide emission because H2 is difficult to observe directly in cold conditions. In millimeter wave maps, molecular clouds appear as bright, clumpy complexes threaded by filaments, with dark cores where starlight is swallowed. These phases are not separate layers stacked neatly, but a cycling ecosystem that constantly exchanges mass and energy. Gas cools and condenses into clouds, then feedback heats and disperses it back into warmer and hotter phases. Shocks, turbulence, and radiation create boundaries that move and fold, like weather fronts colliding and dissolving. The ISM is therefore a machine of phase changes, driven by both gravity and energy injection from stars. The galaxy's rotation sets the stage, but the ISM performs the choreography. Turbulence is one of the key actors, because it can both support and compress gas depending on scale. On large scales, turbulent pressure can resist collapse, delaying star formation and spreading energy. On smaller scales, supersonic turbulence creates dense filaments and knots where gravity can take hold. Observationally, we see this in line widths that exceed thermal speeds, and in filamentary structures revealed by dust emission, the same chaotic motion that prevents global collapse can seed local births. Magnetic fields thread this entire medium, and they are measurable even when invisible, which makes them unusually satisfying to study. We detect galactic magnetic fields through Faraday rotation, where polarized radio waves twist as they pass through magnetized plasma. The amount of twist depends on electron density and the field component along the line of sight, turning distant radio sources into probes. We also detect fields through polarized dust emission, because aligned grains emit and absorb light with preferred orientations. These methods reveal both large-scale structure and tangled turbulence, showing order embedded in chaos. The Milky Way's field has a coherent component that roughly follows the spiral pattern, bending along the disk like a faint invisible scaffold. It also has a turbulent component stirred by supernova, shear and cloud motions, producing reversals and knots. Field strengths are typically a few microgauss in the disk, which sounds tiny until you compare energy densities. In fact, the magnetic energy density is comparable to that of cosmic rays and turbulence, a near equality known as approximate equipartition. That near equality suggests a self-regulating system rather than a minor correction, as if the galaxy prefers a balanced budget of pressures. Magnetic fields matter because they influence how gas collapses and how angular momentum is redistributed. A strong field can provide support against gravity, slowing collapse across field lines and shaping clouds into flattened structures. Ambipolar diffusion and turbulence can allow dense regions to decouple and collapse anyway, because neutral gas can slip past ions tied to the field. The balance is not settled in every environment, so magnetism remains part of the mystery of star formation efficiency. Why does one cloud convert only a few % of its mass into stars, while another forms a cluster? The answer is often hidden in the interplay of gravity, turbulence, and magnetic tension. Magnetic fields also guide cosmic rays, which are another hidden component of galactic motion and pressure. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, moving near the speed of light. Many are accelerated in supernova remnants through shock processes that convert blast energy into particle energy, a mechanism supported by theory and observations. Once injected, they diffuse through the galaxy along magnetic field lines, scattering off irregularities like hikers following a trail of stepping stones. Their paths are tangled, so their arrival directions at Earth do not simply point back to their sources. Cosmic rays fill the disk and halo, and they carry pressure that can drive winds, especially when coupled to magnetic fields. In some models, cosmic ray pressure helps lift gas out of the disk, contributing to a galactic fountain that cycles material. They ionize gas in regions where ultraviolet light cannot reach, especially inside dense clouds shielded by dust. That ionization affects chemistry, enabling reactions that build complex molecules on grain surfaces and in the gas phase. Cosmic rays also heat gas, subtly changing the conditions for collapse and fragmentation, which can shift the mass distribution of forming stars. We infer cosmic rays indirectly, because they are charged and do not point back cleanly, so we look for their fingerprints. We detect their presence through gamma rays produced when cosmic rays collide with gas, creating pions that decay into high-energy photons. We also detect synchrotron radio emission, produced when relativistic electrons spiral in magnetic fields and radiate. These signals map where cosmic rays and magnetic fields overlap, turning the galaxy into a layered image of invisible components. In gamma-ray maps, the plane glows with diffuse emission, tracing interactions between energetic particles and ordinary gas. So the Milky Way's motion is not just stars orbiting a centre, and that is the deeper theme of this chapter. It is stars, gas, fields, and particles exchanging energy and momentum across scales, from parsecs to hundreds of kiloparsecs. Gravity sets the large-scale orbits, but pressure and magnetism shape the small-scale flows that determine where clouds survive. The galaxy is a coupled machine, where different components respond on different timescales and with different kinds of inertia. Stars behave like collisionless test particles, while gas behaves like a compressible fluid that can radiate away energy. At the centre of this machine sits a gravitational anchor we cannot ignore even if we postpone its full story. Motions near the inner parsecs imply a compact mass, far denser than any star cluster could remain without collapsing. We can track stellar orbits around an unseen point, watching them accelerate and swing through tight arcs. Those stars act like test masses in a relativistic neighbourhood, where gravity steepens and time itself becomes part of the accounting. The simplest explanation is a supermassive black hole, inferred from Keplerian motion and extreme central densities. We will not fully enter that engine room yet, because the centre deserves its own chapter and its own atmosphere. For now, the key is what motion lets us know, and what it refuses to reveal even under intense scrutiny. We can measure speeds, dispersions, and coherent streams with extraordinary precision, often down to kilometers per second across vast distances. We can infer mass distributions that explain those motions, including a dominant dark halo that outweighs the luminous disk. We cannot yet identify the dark matter particle, or map the halo's exact shape without ambiguity, because different models can fit the same data. The galaxy gives us constraints, not confessions. Even the visible disk hides complexity in its moving parts, and the complexity is not a flaw but a clue. Spiral patterns may be steady waves or transient segments, and the data can support hybrid pictures that change with radius. The bar reshapes inner orbits and drives non-circular flows that complicate simple rotation models based on circular symmetry. The disk's warp and ripples suggest ongoing interaction, not a settled equilibrium, as if the Milky Way is still responding to recent nudges. When we map the outer gas layer, it bends like a tilted brim, hinting at torques from the halo, satellites, or misaligned infall. This is the Milky Way's central paradox in motion form, and it is what makes the story feel mysterious. We live inside a system we cannot photograph from outside, yet we can weigh it by how it turns, and by how its outskirts move. We can reconstruct past mergers by the trails they left in phase space, even when the merging bodies are long gone. We can detect magnetic order in dust polarization, and cosmic rays in gamma rays, without ever touching them. What other components shape our galaxy, quietly and persistently, while remaining just beyond direct sight? Motion shapes matter, but matter also cycles, and the cycle builds stars. The Milky Way is not only a map of orbits and arms, it is a working chemical factory, quiet, cold, and relentless, turning simple gas into complex worlds. Begin with the raw material, because star formation starts long before any star shines. Most new stars form inside giant molecular clouds, the coldest and densest phase of the interstellar medium. In their interiors, temperatures hover near 10 to 20 Kelvin, only a few degrees above absolute zero. At those temperatures, thermal pressure weakens, so gravity can finally compete with internal motion. In the simplest terms, cold gas cannot push back as effectively, so even gentle compressions can become decisive. From the outside, a molecular cloud can look like an ink stain across the Milky Way's bright band. In visible light, it is a silhouette, a missing piece of the sky. Starfields seem to end abruptly, as if someone erased the background with a soft, dark brush. In infrared, the same region glows softly, as dust re-radiates absorbed starlight as heat. In radio and millimeter wavelengths, it becomes a landscape of structure, filaments, knots, and layered shells. The cloud stops being a void and becomes a terrain, with ridges and valleys carved by physics. These clouds span tens to hundreds of light years, and their masses range from thousands to millions of suns. The largest complexes, like those in the inner spiral arms, contain enough material to form entire clusters and associations. Their average densities can seem modest by Earth standards, yet their sheer volume makes them gravitationally significant. A cloud's fate depends on a delicate balance between self-gravity, turbulence, magnetic fields, and external pressure. Even the galaxy's broader environment matters, because tidal forces and spiral shocks can stretch and squeeze clouds over time. Molecules survive there for one main reason: shielding. Dust grains and the outer layers of gas absorb ultraviolet photons that would otherwise break molecules apart. In exposed regions, hydrogen becomes atomic, carbon becomes ionized, and chemistry resets to simpler forms. In shielded cores, molecular hydrogen dominates, carbon monoxide becomes abundant, and a richer chemical inventory accumulates. The difference is like stepping from sunlight into a cave. Outside, radiation strips complexity away, while inside, fragile bonds persist. That transition is not merely chemical, it is physical. As a cloud becomes molecular, it also cools more efficiently, because molecules and dust radiate energy away. Cooling lowers pressure, which encourages further contraction, which deepens shielding, which allows more molecules to survive. The cloud, in effect, builds its own darkness, an engineered refuge where complexity can grow. It is a feedback loop in miniature, running quietly long before any star begins its own. We cannot usually see cold H2 directly at these temperatures, because it emits weakly in the cold. Instead, astronomers trace it using proxies that are brighter and easier to detect. Carbon monoxide, especially the common isotopolog 12CO, emits in the millimeter band and maps broad reservoirs across the disk. Rarer isotopologs, like 13CO and C18O, help probe denser regions where 12CO becomes optically thick. By comparing these lines, observers infer density, temperature, and motion, turning faint spectra into a three-dimensional diagnostic. Dust provides a second, complementary map. Infrared and submillimeter emission reveals filaments and cores, even where starlight is fully blocked. Dark clouds that erase the optical sky reappear as luminous lanes in far infrared surveys, because dust warmed to tens of Kelvin radiates efficiently. The glow is subtle and granular, like embers spread through smoke. Together, gas lines and dust glow show that star formation is not smooth. It is clumpy, hierarchical, and sculpted by turbulence. A molecular cloud is not a quiet sphere waiting to collapse. Supersonic turbulence, motions faster than the local speed of sound, creates shocks that both support the cloud globally and compress it locally. In one region, turbulent pressure can delay collapse by stirring the gas. In another, converging flows create dense ridges where gravity suddenly gains the advantage. The same chaos that resists collapse can also trigger it. Observationally, this appears as broad line widths, the spectral signature of gas moving in many directions at once. The visual imprint of that process is unmistakable. Long filaments stretch like braided smoke through the cloud, and where filaments intersect, bright cores appear in submillimeter maps. Those junctions are not random decorations, they are gravitational collection points. Gas streams along filaments, feeding the densest knots, and raising their mass until collapse becomes inevitable. Fragmentation follows, producing many cores with a wide range of masses. The pattern hints at a deeper question: how much of the stellar mass distribution is written by turbulence before any star ignites? Magnetic fields add another layer of control. They thread through clouds and can guide gas motion, resisting compression across field lines while allowing flow along them. Polarized dust emission reveals these invisible structures, like iron filings tracing a magnet. In some regions, fields appear strong enough to slow collapse, while in others, turbulence dominates. The outcome is a spectrum of environments, not a single recipe. Even a modest field can change the geometry of collapse, shaping disks, jets, and the alignment of filaments. Collapse begins hidden, because dust makes the earlier stages optically dark. A protostar forms at the center of a collapsing core, and it grows by accreting gas through a rotating disk. The disk is not an accessory, it is a consequence of angular momentum. Even a tiny initial spin becomes significant as the core contracts, forcing material into orbit rather than straight in fall. The disk also becomes a chemical and thermal gradient, with hot inner regions and icy outer zones that foreshadow later planet building. In these embedded stages, the scene is more felt than seen. infrared images show faint points buried in glowing dust, while radio interferometers resolve disks only a few hundred astronomical units across. Around them, envelopes of cold gas still fall inward, feeding the disk like a slow, spiraling rain. The protostar itself can brighten in bursts, as clumps in the disk dump material onto the forming star. Those bursts leave fingerprints in the surrounding ice chemistry as sudden heating resets reactions and then freezes them again. Jets and outflows appear early, carving narrow channels through the surrounding envelope. They are launched by magnetic fields anchored in the disk and twisted by rotation. The jets can reach hundreds of kilometers per second, punching through the cloud like needles. Their slower, wider outflows sweep up gas, creating bipolar cavities that glow in shocked molecular emission. In images, these cavities look like opposing searchlights, except the beams are carved voids in dust and gas. These outflows are not side effects. They are part of how a forming star regulates its own growth, because they carry away angular momentum that would otherwise halt accretion. They also inject turbulence back into the cloud, stirring the very medium that formed the star. In a crowded cluster, many such outflows overlap, turning a calm cloud into a churning, feedback-driven environment. One can almost imagine the cloud as a breathing organism, inhaling gas into cores and exhaling momentum through jets. Star formation often needs triggers, because the Milky Way is a shearing, pressurized disk. Spiral arms act like traffic jams in orbital flow, compressing gas as it enters a denser region. The compression raises density, encourages cooling, and helps assemble molecular clouds from more diffuse material. As the gas exits the arm, shear and feedback can tear clouds apart again. This is not a static spiral pattern painted on the disk, but a moving wave that organizes where clouds can persist. Supernova shocks provide another trigger, and their influence can be dramatic. A blast wave expands into the interstellar medium, sweeping up gas into a shell. Where the shell cools and thickens, it can fragment into dense clumps that become new star-forming sites. In that way, a star's death can help ignite the next generation, though the timing and geometry must be just right. If the shock arrives too early, it can shred a cloud. If it arrives late, it may simply pass through empty space. Cloud-cloud collisions can also drive rapid compression, especially where orbital flows converge. In these encounters, two large reservoirs of gas meet at supersonic speeds, and their interface becomes a shock-compressed layer. Dense structures can form quickly, and massive star formation may be favoured in the highest pressure zones. Yet collisions can also disrupt clouds, depending on impact speed and internal structure. The same event can create a dense ridge in one place, and a dispersing spray of gas in another. The key is that feedback is double-edged. Compression can create new stars, but energy injection can also disperse the very clouds that might have formed them. Radiation from massive stars heats and ionizes gas, increasing pressure and driving expansion. Stellar winds add momentum and turbulence, and they excavate cavities that halt accretion onto nearby cores. The balance depends on distance, shielding, and the cloud's internal density structure. Small differences that decide whether a core survives. To picture this, imagine a newborn cluster as a bright furnace inside a fog bank. Ultraviolet photons carve an H2 region, a bubble of ionized hydrogen that glows in emission lines. The boundary where ionized gas meets neutral material becomes an ionization front, sharp and luminous. Along that front, dense clumps cast shadows, and pillars form as softer gas erodes away. In time-lapse, the bright rim creeps forward, eating into the cloud while leaving stubborn islands behind. Ionization is not only a change of state, it is a change of force. Ionized gas is hotter, often near 10,000 Kelvin, and its pressure can exceed that of the surrounding cold cloud by orders of magnitude. The hot gas expands, driving shocks into the neutral material. Those shocks can compress nearby ridges into new dense cores, even as the overall cloud is being destroyed. It is creation under duress, stars forming in the very act of being exposed. This is the Milky Way's ecology in miniature. Star formation is not a one-way conversion of gas into stars. It is a loop where stars reshape the gas, and the reshaped gas sets the next generation's conditions. The galaxy self-regulates because too much star formation produces too much disruption, and too little leaves gas cold enough to gather again. The disk behaves less like a factory line and more like weather, with cycles, thresholds, and sudden local storms. Regulation shows up in numbers as well as images. Only a small fraction of a cloud's mass becomes stars before feedback disperses the rest. The typical efficiency can be a few percent in many regions, though it varies with environment. That inefficiency is not a failure, it is a stabilizer, preventing the Milky Way from consuming its gas in a single bright episode. It also means the galaxy can keep forming stars for billions of years, rather than burning out quickly like a brief flare. Case studies make the cycle concrete, because different regions show different stages at once. The Orion Nebula is a nearby laboratory where an H2 region sits beside dense molecular gas. It is close enough that we can resolve protoplanetary disks, the so-called proplids, silhouetted against glowing gas. Orion shows how massive stars illuminate and erode their birth environment, while new stars still form in adjacent shielded structures. It also carries a historical weight, because it helped define the modern picture of star formation as an ongoing galactic process. In wide-field views, Orion is a tapestry of contrasts. Blue-white stars blaze at the centre, while dark lanes of dust cut across the nebula like torn fabric. Infrared reveals embedded clusters still wrapped in their natal cocoons, and radio maps trace cold gas behind the bright curtain. The region demonstrates clustering because many young stars form together rather than alone. Even the brightest glow is edged by darkness, a reminder that the most active sites are often the most obscured. Orion also teaches a subtler lesson about timing. Some stars there are already clearing their surroundings, while others are still accreting. The nebula is not a single moment frozen in time, it is a layered sequence. Star formation proceeds in waves across the cloud, influenced by earlier feedback and by the cloud's own internal flows. The question that lingers is how synchronized a cluster can ever be when each star experiences its own local conditions. The Carina Nebula pushes the feedback story harder. It hosts very massive stars whose radiation and winds dominate the local energy budget. Carina's central clusters include stars so luminous that their photons shape the entire region's geometry. In optical images, the nebula looks like a stormlit coastline with bright ridges and dark bays. In X-rays, hot plasma fills cavities where winds collide and shock. The scene suggests an engine room where mechanical power is converted into heat, light, and expanding shells. Carina shows pillars, cavities, and ionization fronts that mark where hot plasma meets cold molecular material. The pillars are not merely scenic. They are pressure-confined remnants of denser gas. Their tips often harbour young stars, suggesting that compression has triggered collapse. Yet the same radiation that may trigger some stars also strips mass from disks and evaporates exposed clumps. In a single frame, you can see both the promise of new suns and the erosion of their raw material. It highlights a central tension in galactic growth. The same massive stars that enrich the galaxy also threaten to shut off nearby star formation. Their winds can clear gas quickly, shortening the window for low-mass stars to finish accreting. Their ultraviolet light can photodissociate molecules, undoing the chemistry that cold clouds depend on. Carina is a reminder that creation and destruction are intertwined processes. It also hints at why massive stars, though rare, can dominate the fate of an entire region. The Eagle Nebula captures a more iconic snapshot of erosion and survival. Dense columns persist because their cores are shielded, even as their surfaces are photo-evaporated. In close-up, the pillars look like stone, but they are gas and dust shaped by radiation. Bright rims trace ionization fronts, while darker interiors hide the coldest, densest material. The contrast is so sharp that it feels architectural. Walls, arches, and narrow spires sculpted by invisible light. The scene is not static, because the pillars are temporary structures in a moving radiation field. Material flows off their surfaces in a slow, glowing wind, and the pillars gradually thin and retreat. Embedded cores can outlive the pillars that protect them, emerging later as exposed young stars. Eagle helps illustrate why dust is both obstacle and ingredient, hiding the earliest collapse while enabling the chemistry that makes collapse possible. It also invites a quiet question. How many stars form just in time before their shelters are stripped away? Most stars are born in groups because clouds fragment into many cores at once. In the densest regions, cores form within a shared gravitational potential, and their interactions matter. Close encounters can truncate disks, alter orbits, and even eject stars from the cluster. The birth environment is therefore not only a gas problem, it is also a dynamical one. A planetary system's earliest architecture may be shaped as much by neighbours as by its own disk physics. Some groups are gravitationally bound and become open clusters. Others are looser and become associations, where members share an origin but not a long-term common orbit. The distinction matters because it determines how long a birth family stays recognisable. It also affects how long young planetary systems remain in crowded neighbourhoods. In bound clusters, repeated encounters can continue for tens of millions of years, slowly rewriting the early history of disks. Open clusters can survive for tens to hundreds of millions of years, sometimes longer, but most eventually disperse. Internal dynamics slowly evaporate members as repeated gravitational encounters transfer energy and push lighter stars outward. External tides from the galactic potential strip stars away, especially as clusters orbit through the disk. Encounters with giant molecular clouds can accelerate disruption because a passing cloud can gravitationally shock a cluster. The process is subtle in any single orbit, yet relentless over many. Over time, clusters dissolve into the field, and their stars become part of the disk's background glow. The process is gradual, like smoke thinning into air, and it is difficult to reverse. Yet even after dispersal, a cluster's former members can retain a shared chemical fingerprint. Their atmospheres preserve the elemental ratios of the gas from which they formed. That chemical memory becomes a kind of genealogy, written not in names but in magnesium, silicon and iron. Associations disperse even faster because they are only weakly bound from the start. Their members drift apart within a few tens of millions of years, leaving only a kinematic and chemical trace. In surveys, associations can appear as moving groups, stars sharing similar velocities across the sky. But the signature fades as the galaxy's gravitational irregularities stir orbits over time. What begins as a coherent stream becomes, slowly, a statistical hint. This is why the night sky is deceptive. Many stars that look isolated may be former cluster members whose siblings are now scattered across the disk. The Milky Way's rotation stretches groups into streams, and spiral structure perturbs them further. What begins as a tight family portrait becomes, after hundreds of millions of years, a dispersed population. The sky's apparent randomness hides a history of togetherness that has been stretched thin. That implication reaches directly to our own origin. The Sun likely formed in a cluster or association, because solitary star formation is less common than group formation. Evidence comes indirectly, from the solar system's composition and from models of typical star-forming environments. Some short-lived radioactive isotopes in early solar system material hint at nearby massive stars suggesting a crowded neighbourhood. If a supernova contributed material, it also implies proximity, close enough to enrich, far enough to avoid destruction. If so, the Sun's siblings have been lost to differential rotation, scattering, and billions of years of mixing. The disk is not a static stage, it is a moving fluid of orbits. Stars migrate radially, their guiding centres shifting due to interactions with spiral arms and other perturbations. Over time, even siblings born together can end up thousands of light years apart. The thought is unsettling and elegant. Family, dispersed by gravity, yet still orbiting the same galactic centre. Chemical tagging offers a partial recovery method, because siblings can share detailed abundance patterns. High-resolution spectroscopy can measure dozens of elements, building a multidimensional chemical profile. In principle, that profile can identify stars that formed from the same well-mixed cloud. But the disk is an efficient blender, and the longer the time, the harder the reunion. The deeper question is whether any signature can remain unique, once billions of stars have sampled similar mixtures of enrichment. To understand what these birthplaces produce, we need a compressed guide to stellar evolution. A star's path is set mainly by mass, because mass sets core pressure and temperature. Low-mass stars ignite hydrogen gently and burn it slowly, staying on the main sequence for billions to trillions of years. High-mass stars burn fast, shine intensely, and die young, often within a few million years. Mass is destiny in the strictest physical sense because it sets the thermostat of nuclear reactions. After the protostar phase, hydrogen fusion begins in the core, and the star reaches the main sequence. The ignition is not an explosion, it is a transition to stable energy production. For most of its life, a star balances gravity with pressure from hot gas and the energy released by fusion. This balance, hydrostatic equilibrium, is the quiet contract that defines a star's long adulthood. Even small changes in core conditions are corrected by expansion or contraction, a self-adjusting stability that can last for eons. When core hydrogen runs low, the balance shifts. The core contracts and heats, while the outer layers expand and cool, and the star becomes a giant or supergiant. Fusion does not stop. It reorganizes into shells around the core. Each shell burns a different fuel, and the star becomes a layered structure, like an onion of nuclear reactions. The outer atmosphere grows tenuous and extended, making giants luminous but fragile, easily shaped by winds and pulsations. The details depend on mass, and the consequences are profound. A sun-like star will expand into a red giant, ignite helium into carbon and oxygen, and eventually shed its outer layers. The exposed core becomes a white dwarf, a dense remnant supported by electron degeneracy pressure. A more massive star continues to higher temperature burning stages, producing heavier elements in successive shells. In those massive interiors, the timescales compress dramatically, and the final stages race toward collapse. The Milky Way's light changes over time because the mass distribution of newborn stars is not uniform. Massive stars dominate ultraviolet light and ionization, but they are rare and short-lived. Intermediate mass stars contribute much of the visible starlight over longer spans, shaping the galaxy's broad optical appearance. Low-mass stars contribute faintly but persist, and they accumulate over cosmic time. The galaxy's glow is therefore a weighted average of brief brilliance and long endurance. This distribution is often summarized as an initial mass function, a statistical rule describing how many stars form at each mass. It is one reason the galaxy's star formation rate cannot be judged by optical brightness alone. A region can form many low-mass stars while remaining visually modest. Conversely, a few massive stars can make a region blaze, even if the total mass in new stars is not enormous. The mismatch between light and mass is a recurring trap in astronomy. What looks dominant is not always what is most abundant. Element production is the hidden output of this evolution, and it is the chapter's central alchemy. In stellar cores, fusion builds elements up to iron, because iron marks a turning point in nuclear energy yield. Lighter elements release energy when fused, supporting the star against collapse. Beyond iron, fusion consumes energy, so it cannot power a stable core. This boundary is not arbitrary. It is set by nuclear binding energy, the deep accounting of what reactions can pay their own gravitational bills. The path to iron is itself a sequence of thresholds. Hydrogen fuses into helium, helium into carbon and oxygen, and in massive stars carbon and oxygen can fuse into neon, magnesium, and silicon. Each stage requires higher temperatures and proceeds faster than the last. Near the end, silicon burning can build iron group elements in days, a brief and intense finale. The star is then living on borrowed time. When the core can no longer support itself, collapse is swift, and the outward explosion is the violent answer. When massive stars die, they return those elements to the interstellar medium. Core collapse supernovae eject oxygen, silicon, and other alpha elements, and they seed surrounding gas with newly forged material. The explosion also drives a shock that sweeps up ambient gas, mixing ejecta into the surrounding medium. Over thousands of years, the remnant expands, cools, and merges with the galaxy's broader gas reservoir. The mixing is imperfect at first, which is why nearby newborn stars can inherit slightly different chemical ratios. Type Ia supernovae, from white dwarfs in binary systems, contribute large amounts of iron on longer timescales. Because they can occur long after star formation, they enrich the disk in a delayed way. The different delay times imprint chemical clocks into the disk, which later chapters use as galactic archaeology. By comparing alpha elements to iron, astronomers infer the relative influence of rapid core collapse events versus slower type Ia contributions. This method grew from decades of stellar spectroscopy, a tradition that turned starlight into a record of ancient explosions. Some of the heaviest elements require more extreme events. Rapid neutron capture, the R process, builds gold, platinum, and other heavy nuclei in environments with intense neutron flux. Neutron-star mergers are now confirmed as major R process sites, and their gravitational wave signatures have linked them to bright kilonova afterglows. Despite being rare, they can enrich large regions because their ejecta are neutron-rich and efficient at building heavy nuclei. In a sense, precious metals are the fossils of catastrophes, scattered thinly through the disk. Some core collapse supernova channels may also contribute, and the balance remains an active research frontier. The Milky Way's chemical story is therefore a mosaic of sources, each with its own frequency and yield. The question is not only where elements form, but how well they mix into the gas that forms later stars. Even small inhomogeneities can persist long enough to be recorded in stellar atmospheres. The galaxy remembers its past not as a single average, but as a textured distribution of outcomes. This is the biological prelude embedded in astrophysics. The carbon in cells, the oxygen we breathe, and the iron in blood were assembled in earlier generations of stars. The Milky Way is not just where we live. It is part of what we are, because our atoms are recycled galactic material. If the galaxy's chemistry had unfolded differently, the periodic table available to life would have been different as well. Dust is the quiet mediator between physics and chemistry, and it deserves its own accounting. Dust grains are mostly silicates and carbonaceous material, often coated with ices in cold regions. Typical grain sizes cluster around micron and submicron scales, small enough to interact strongly with visible light. That size range makes dust efficient at scattering and absorbing, which is why the galactic plane is opaque in optical bands. The same grains that hide the galaxy also cool it, because they radiate efficiently in the infrared. Dust is also a historian of violence. Grains can form in cool outflows from evolved stars and in supernova ejecta, then travel through the interstellar medium for millions of years. Along the way, they are processed by shocks, sputtering and collisions that can shatter larger grains into smaller fragments. In dense clouds, grains can grow again by accreting mantles of ice and by sticking together into fluffy aggregates. This constant grinding and regrowth changes how dust absorbs light, subtly altering the colours of starlight passing through. Dust blocks visible light, but it also creates surfaces where molecules can form. On grain surfaces, hydrogen atoms meet and combine into H2 far more efficiently than in the gas phase. Ices on grains host reactions that build water, methanol, and more complex organics. In the deep cold, these ices can preserve chemical products for long periods, like a frozen archive of reactions. The chemistry is slow, but the timescales are long and the cloud provides patience. When grains are warmed or shocked, those molecules can be released back into the gas. A passing shock can sputter ice mantles, and a nearby young star can heat dust enough to sublimate ices. The result is a sudden chemical enrichment of the gas, which can be detected as bright spectral lines. In this way, chemistry becomes a tracer of physical change, revealing where energy has recently been injected. A spectrum becomes a weather report, telling us where the cloud has been disturbed. Dust also changes how we measure the Milky Way, tying back to the central question. Extinction reddens and dims starlight, and it can mimic distance effects if not corrected. Early astronomers struggled with this, mapping star counts and assuming darkness meant emptiness. Only later did the role of interstellar dust become clear, reshaping our understanding of the galaxy's structure. That realization was a turning point, an admission that the galaxy hides itself, and that observation must adapt. Infrared surveys cut through much of the obscuration, but even infrared can fail in the densest cores. Radio and millimeter observations bypass dust almost entirely, letting us trace gas where optical maps show only darkness. Multi-wavelength astronomy is therefore not a luxury, it is a necessity. Each band reveals a different physical component, and only their combination approaches a complete picture. The Milky Way becomes legible only when we read it in many alphabets of light. Supernovae are both destroyers and builders in this dust story. Their shocks can shatter grains in hot, fast flows, reducing dust locally and returning material to the gas phase. Yet supernova ejecta can also condense new dust as they expand and cool. Observations of young remnants show dust forming surprisingly early, though survival through later shocks is still debated. The answer matters, because dust survival sets how quickly galaxies can become opaque and chemically active. The net dust budget depends on destruction rates, formation rates, and growth in dense clouds, and those balances are still being refined. Dense molecular regions may be the main sites where dust mass grows, as atoms stick to grain surfaces and mantles thicken. In that sense, clouds are not only star factories, they are dust factories as well. The galaxy's opacity, chemistry, and cooling are all tied to this cycling of solids. It is an economy of tiny grains, yet it governs the visibility of spiral arms and the efficiency of starbirth. Supernovae also sculpt the interstellar medium on large scales. In the Milky Way, the supernova rate is on the order of a few per century, though many are hidden by dust and go unrecorded in visible light. Historical records from other cultures occasionally capture bright supernovae, reminders that the galaxy's violence sometimes breaks through the veil. Most events, however, occur behind the thick lanes of the disk. Even when we do not see them, their energy still spreads, reshaping gas far beyond the original blast site. Their remnants expand as shock waves, sweeping up shells and heating plasma to X-ray temperatures. The interior can reach millions of Kelvin, glowing in high-energy emission. The outer shock compresses gas, amplifies magnetic fields, and leaves behind filamentary arcs. Over tens of thousands of years, the remnant slows, cools, and merges into the surrounding medium, contributing to the galaxy's hot diffuse phase. In radio images, these remnants appear as ghostly rings, the afterimages of a star's final moment. Remnants can merge into superbubbles when multiple massive stars die in the same region. In an OB association, winds and supernovae overlap, inflating cavities hundreds of light-years across. The walls of these cavities can become dense and fragmented, sometimes forming new clouds. Superbubbles can also vent hot gas into the galactic halo, linking disk star formation to the larger galactic environment. The disk is not sealed. It breathes, exchanging energy and material with the space above it. These remnants are also particle accelerators. Shock fronts can accelerate cosmic rays through diffusive processes, converting kinetic energy into relativistic particles. Those particles then interact with gas and radiation fields, producing gamma rays and synchrotron emission. In this way, supernovae connect star formation to the high-energy Milky Way mapped in other wavelengths. The galaxy's most violent events leave behind not only shells, but invisible storms of fast particles. Cosmic rays matter because they penetrate where light cannot. They ionize dense molecular gas at low levels, influencing chemistry and coupling gas to magnetic fields. Even deep inside a cloud, where ultraviolet photons are absent, cosmic rays can initiate reaction chains. The galaxy's energetic particles therefore participate in the same cycle, linking explosions to cold chemistry. A cloud's interior is never completely isolated because particles can reach where photons fail. Feedback loops operate across scales, and they are the chapter's organizing principle. Radiation pressure pushes on dust and gas, especially near massive stars and clusters. Stellar winds inject momentum and carve cavities that can channel later supernova blasts. Ionization fronts create sharp boundaries where neutral gas becomes plasma, and those boundaries can compress adjacent material into new star-forming ridges. The result is structure with edges, bright rims, dark cores, and expanding bubbles that mark where energy meets matter. Yet the same feedback can also quench star formation by dispersing molecular gas. If gas is heated and ionized, it expands and becomes harder to recollapse. If turbulence is driven too strongly, dense cores can be shredded before they finish collapsing. The Milky Way's star formation efficiency stays low in many regions, suggesting regulation is the default, not the exception. The galaxy seems to prefer moderation, as if it is tuned to avoid both runaway collapse and complete sterility. This raises a quiet question about the galaxy's character. Is the Milky Way conservative by nature, forming stars slowly to preserve its gas reservoir? Or is it simply constrained by physics, forced into moderation by feedback and shear? The answer is partly historical, because the galaxy's past star formation rate has changed over billions of years. The present-day disk is a mature system, not a youthful starburst. Its calm is earned, shaped by long-term balancing acts rather than a lack of raw material. Yet the galaxy keeps forming stars because regulation is not suppression. Gas continues to flow through spiral structure, accumulate in clouds, and cool in shielded interiors. The disk's rotation and shear constantly rearrange where compression happens. Over millions of years, the same region can cycle from quiet molecular reservoir to bright H2 region to evacuated bubble. The cycle is slow by human standards, but fast by galactic ones, a repeating rhythm written across the arms. In time-lapse, the Milky Way would look alive. Dark clouds would condense, brighten at their edges, and then be hollowed out from within. New clusters would flare into view, then drift apart as their natal gas disperses. Supernova shells would ripple outward, overlapping like rings on water. The galaxy's calm appearance hides this continuous slow-motion weather. What looks like a static band of light is, in reality, a shifting pattern of birth lines and shock fronts. The quiet majority of stars are not the luminous beacons that define nebular photographs. Red dwarfs are the most common stars in the Milky Way, and they dominate the star count even if they do not dominate the light. Their low masses mean slow fusion and extremely long lifetimes, often far longer than the current age of the universe. In the far future, when massive stars are long gone, red dwarfs will still be burning steadily. Their faintness is deceptive, because their sheer number makes them the galaxy's main stellar population. They're also key to the galaxy's long-term stability. Because they live so long, they preserve the chemical record of the gas at their birth. Many red dwarfs formed early in the Milky Way's history, and they still orbit today, faint but numerous. Their abundance makes them the galaxy's enduring population, the background against which brighter, shorter-lived stars come and go. In a sense, they are the Milky Way's archival storage, quietly holding snapshots of ancient composition. That fact changes the galaxy's destiny in a subtle way. The Milky Way's brightness and colour will evolve as short-lived blue stars disappear and long-lived red stars accumulate. Star formation will eventually decline as gas is consumed, heated, or expelled, though the timescales are long. The galaxy's future light may be dimmer and redder, even if its mass remains bound. The night sky of a distant future would still be full of stars, yet less dramatic in colour and contrast. Even now, the disk's gas supply is finite, and each generation of stars locks some material away. Not all gas becomes permanently unavailable, because stellar winds and supernovae return a fraction to the interstellar medium. Still, the overall trend is toward gradual depletion and heating. The Milky Way is not running out of time soon, but it is not infinitely renewable either. The same recycling that enables star formation also slowly changes the reservoir's temperature, composition, and ability to cool. This chapter's facts point back to the same mystery that opened the series. We live inside a dusty disk that hides its own machinery, yet we can reconstruct the machinery by combining wavelengths, chemistry, and dynamics. Molecular clouds explain where stars begin, and feedback explains why the process is inefficient and episodic. Stellar evolution explains where elements come from, and dust explains why the galaxy both conceals and enables its own creation. When we assemble these pieces, the Milky Way stops being a backdrop and becomes a system, self-modifying, self-limiting, and endlessly inventive. There is also a philosophical edge to this reconstruction. We infer invisible molecules from faint lines, and we read ancient explosions from elemental ratios in starlight. We watch newborn stars through curtains of dust, then trace their descendants across the disk. The Milky Way's story is written in matter that moves, transforms, and returns, again and again. And if the same atoms can pass from cloud to star to shockwave and back, what does it mean to call any structure permanent? Star birth and death are local dramas, but the Milky Way also hosts extreme phenomena. The next descent is inward, toward a place our eyes cannot simply look, because the view is blocked and the physics is unforgiving. We are not travelling to a single star or nebula. We are approaching a gravitational crossroads where the galaxy's traffic converges. In that crossroads, orbits crowd together, gas streams intersect, and the bookkeeping of mass becomes brutally precise. The galactic centre sits behind the disk's thickest dust lanes, so visible light fails first, and it fails decisively. Along the plane, interstellar grains, silicates, carbon-rich particles, and icy mantles act like smoke in a spotlight, dimming and reddening everything behind them. Many grains are roughly the size of visible wavelengths, so they scatter blue light efficiently and leave the inner galaxy washed in brownish haze. Optical maps show a bright bulge cut by darkness, and the true nucleus stays hidden behind that jagged seam. Dust grains absorb and scatter short wavelengths, turning the inner galaxy into a silhouette that looks like absence. In the visible band, the centre is not missing, it is censored. This concealment has a history that shaped how we imagined our own galaxy. Early astronomers could chart the Milky Way's star clouds and measure the bulge's glow, yet the central engine remained a blank patch in the most literal sense. The bulge itself was debated. Was it a structure, or simply the line-of-sight thickening of the disk's star field. Even when the bulge was recognized as real, its deepest core was still an inference drawn from symmetry and star counts. The central question returns in a sharper form because it refuses to stay philosophical. What is the Milky Way really when its core is concealed? Astronomy answers by changing the alphabet of light, and by admitting that the eye is only one detector. Infrared penetrates much of the dust and reveals dense star fields toward the nucleus, where the bulge becomes a crowded tapestry of points. In near-infrared, extinction drops dramatically, because longer wavelengths slip between dust grains rather than ricocheting off them. Radio waves pass through almost unimpeded and can mark compact sources precisely, even when the optical sky is blank. Together, infrared astrometry and radio interferometry build a coordinate system inside the fog. The center is found by measurement, not by appearance. In practice, this means instruments become translators between hidden structure and human intuition. Adaptive optics corrects atmospheric blur in real time, letting telescopes resolve individual stars where the sky would otherwise smear into a single glow. Interferometers link antennas across continents, turning Earth into a single virtual dish with the resolving power of a planet. The inner galaxy stops being a blurred glow and becomes a map of points, motions, and spectra, each star a moving test particle. We do not merely see the center, we triangulate it, and we do so repeatedly until the solution becomes unavoidable. In radio, one source dominates the story, and it does so with stubborn consistency. Sagittarius A sits at the dynamical center, compact and bright at centimeter wavelengths, even though it is faint in most other bands. Its position is fixed against distant quasars, making it a stable reference point for the entire inner coordinate grid. That anchoring matters because quasars are effectively motionless on human timescales, their apparent drift measured in microarc seconds. Stars and gas orbit around that location, not around the brightest optical patch in the bulge. The Milky Way's heart is defined by motion, echoing the earlier chapter's rule. The name itself carries a clue, and it also carries the history of discovery. Sagittarius A was originally a broader radio region, a busy neighbourhood of emission that included thermal gas and supernova remnants. The asterisk was added later, an editorial mark for something special and unusually compact, a point-like source inside a crowded field. It is a tiny beacon in a sky full of confusion, and it sits where the galaxy's gravitational bookkeeping balances. Even the punctuation feels like a whisper. Here is the object that matters. Sagittarius A is best explained as a supermassive black hole, and the argument is built from gravity rather than spectacle. Its mass is about 4 million times the Sun's mass, concentrated into a region smaller than our solar system, and that concentration is the key. That mass is not guessed from brightness, because the source is faint today and often drowned by surrounding emission. It is inferred from gravity, using stars as test particles in a deep potential well. The evidence is geometric, repeated, and hard to evade. Gravity leaves signatures that light cannot fake, because orbits are honest even when sources are dim. If a bright cluster were responsible, it would still need to explain the same orbital speeds at the same radii. If a cloud of unseen objects were responsible, it would have to remain stable for millions of years without spreading out or collapsing. The center forces a simple question. What can hold 4 million suns worth of mass in such a small volume without shining like a star? In astronomy, that question has a short list of answers. The key actors are the S-stars, fast stars within a light year of the center, and they move like needles on a compass. They follow tight, highly eccentric orbits that can be tracked over decades, turning human patience into a scientific instrument. Their paths are not gentle circles, they are stretched ellipses, like comets bound to a massive sun but with far higher speeds. The star S2 completes an orbit in about 16 years, a human timescale for galactic dynamics that still feels almost impossible. Near pericenter, S2 reaches thousands of kilometers per second and swings past the unseen mass, close enough that the orbit seems to graze the abyss. The orbit closes around a point that emits little light, yet dictates everything nearby. Watching these stars is like watching a clockwork mechanism reveal its hidden spring, because the pattern repeats and the center never flinches. Night after night, the same points of light shift against the background, and the shifts are small enough to demand exquisite calibration. Their velocities are measured through Doppler shifts, and their positions are measured in milliac seconds. The angle a coin would subtend across continents. Over time, the full three-dimensional orbit emerges, inclination, eccentricity, and orientation, until the geometry locks into place. The centre is not guessed, it is solved. From those orbits, the central density becomes extreme, and the numbers are what make the conclusion so stark. No stable cluster of ordinary objects can pack that much mass into that small volume for long, because gravity would turn the cluster into its own enemy. Alternatives like dense star clusters would evaporate or collapse under their own interactions, as close encounters exchange energy and fling members outward. Collisions, gravitational encounters, and relaxation would either puff the cluster up or drive it into catastrophic collapse, and both outcomes contradict what we see. The simplest model is a black hole, because it naturally concentrates mass without needing light. The Milky Way's core becomes a direct test of a concept once considered unobservable. This is where the argument becomes almost unavoidable, because every alternative must imitate the same compactness. To mimic a black hole, a cluster would need to be made of dark remnants, white dwarfs, neutron stars, stellar black holes, packed to extraordinary densities, yet such a cluster would be dynamically unstable, and it would produce detectable effects over time, including collisions and gravitational scattering that should smear the mass distribution. The S-star orbits show a point-like mass, not a fuzzy distribution, and the residuals punish extended models. The galaxy's centre behaves like a single object. Event horizon scale comparisons make the abstraction tangible, because they translate mass into a boundary you can imagine. A 4 million solar mass black hole has a Schwarzschild radius of roughly 12 million kilometers, a distance that sounds large until you compare it with planetary orbits. That is small compared with the Earth, sun distance, yet enormous compared with any star's core, which is why the term supermassive is not poetic. If you placed it where the sun sits, the event horizon would still fit well inside Mercury's orbit, leaving the rest of the solar system untouched in size but not in gravity. From 26,000 light-years away, the angular size is tiny, demanding interferometry at the edge of technique. The core's most important boundary is physically small but dynamically dominant. The event horizon is not a surface, and that distinction matters when we picture what a black hole is. It is a boundary in space-time, a point of no return for light and matter, defined by escape speed exceeding the speed of light. Outside it, gravity can be resisted with enough speed and angular momentum. Inside it, every path leads inward, regardless of thrust. The horizon is defined by geometry, not by substance, which is why it can be described without describing any material. In the galactic centre, that geometry becomes a target for observation. Relativity is not a distant theory here. It becomes part of the orbit fit, embedded in the data reduction like a required correction. At pericenter, S2's light is gravitationally redshifted, and time dilation becomes measurable, because the star is moving fast and sitting deep in the potential. Observations detect the relativistic redshift and transverse Doppler effect in the spectra, separating them from the simpler Newtonian Doppler shift. In plain terms, the star's light is stretched because it climbs out of a deeper gravitational well, and because the star's own clock runs slightly slow. The orbit also precesses, shifting its closest approach point over time beyond Newtonian expectations, like a rosette rather than a closed ellipse. These are not artistic claims, they are numbers extracted from repeated passages. The measurements are subtle, yet they are decisive, because the deviations accumulate where the gravity is strongest. Spectral lines shift by amounts that match Einstein's predictions within uncertainties, and the uncertainties shrink as instrumentation improves. The timing of pericenter passages can be compared against models with and without relativistic corrections, and the wrong model drifts out of phase. Each orbit is a test, and each test narrows the space for alternatives, because nature does not negotiate with preference. When a star swings past the center, space-time itself becomes part of the data. This makes the galactic center a laboratory for gravity, not in the metaphorical sense but in the operational one. The same equations that describe black holes elsewhere are tested with stars we can track individually, rather than with unresolved blobs in distant galaxies. The measurements constrain the central mass, the distance to the center, and possible extended dark mass that might lurk among the stars. They also limit how much unseen matter can hide inside the S-star region, without spoiling the orbits, which is a powerful negative result. Precision does not end mystery. It narrows where mystery can live. It also clarifies what kind of mystery remains, because knowing the mass does not mean knowing the environment. The mass is known with impressive accuracy, yet the region around it is messy, luminous, and turbulent in ways a simple diagram cannot capture. Gas, magnetic fields, and stellar winds complicate the clean ideal of a lone black hole sitting in vacuum. The centre is both a textbook example and a real place, and real places rarely behave like clean diagrams. The physics is exact, but the setting is alive. Around the black hole sits a dense environment that is not quiet, even when the black hole itself barely glows. The nuclear star cluster packs millions of stars into a small volume, and its light is a constant shimmer in infrared surveys. In infrared images, the field looks almost granular, as if the bulge has been ground into glitter and poured around a single dark drain. Stellar densities rise steeply toward the centre, increasing encounter rates and collision probabilities, and turning long-term evolution into a statistical melee. Close interactions can exchange partners, harden binaries, and eject stars at high speed, producing hypervelocity runaways. The centre is a gravitational pinball machine, and its statistics matter. In such a crowded region, even the definition of neighbour changes, because the typical distances shrink to scales we associate with planetary systems. A star that would drift alone in the solar neighbourhood may pass within a few hundred astronomical units of another star here, close enough for repeated perturbations. Over long times, repeated tugs reshape orbits and redistribute energy, a process known as relaxation that slowly reorders the cluster. The cluster evolves not only through stellar aging, but through constant gravitational negotiation, where no orbit is guaranteed permanent. The centre is old, but it is never settled. The nuclear cluster may also hide intermediate mass black holes, and the possibility is tempting because it bridges a gap in black hole demographics. Such objects could form from runaway stellar collisions in dense clusters, or arrive through infalling clusters that spiral inward over time. If present, they would perturb stellar orbits and heat the cluster dynamically, leaving subtle fingerprints in velocity dispersions and accelerations. Searchers look for tiny departures from smooth motion, unusual kinematic substructures, and transient accretion signatures that would flare and fade. The evidence is suggestive in places, but not yet decisive, which keeps the idea alive. The idea is compelling because it fits the setting, where density makes unlikely events merely rare instead of impossible. Dense clusters can drive massive stars into repeated mergers, building something heavier than ordinary remnants before supernovae can disrupt the process. Over time, the Milky Way's centre could collect these objects like debris in a river eddy, sinking inward through dynamical friction. If they exist, they would add texture to the gravitational potential, small ripples on top of a dominant central mass. Even a ripple can matter when orbits are tight. The centre is also embedded in gas that behaves differently than disk clouds, because the gravitational and magnetic environment is harsher. The central molecular zone is a dense turbulent reservoir spanning the inner few hundred parsecs, and it holds a significant fraction of the galaxy's dense molecular gas. It contains massive molecular complexes, filaments, and ring-like structures shaped by the bar's inflow, where orbits crowd and shocks form. In radio maps, the gas appears as bright arcs and knots, threaded by darker lanes of dust that silhouette against infrared glow. Gas temperatures and velocity dispersions are higher than typical disk values, hinting at constant stirring and heating. The chemistry is unusual, with shock tracers and complex molecules appearing in abundance. This is not the calm, cold molecular gas of the outer spiral arms, where clouds can drift for long times. The CMZ is stirred by shear, compressed by orbital crowding, and battered by feedback, so even dense gas can feel unsettled. Turbulence broadens spectral lines, and that broadening is a clue to internal motion, like wind noise in a microphone. The gas is dense, yet it behaves as if it is constantly being shaken, resisting the simple collapse that would normally form stars. The centre feels like a storm system that never fully dissipates. This region is both fuel and barrier, and that dual role is one of its defining contradictions. Gas is driven inward by bar torques, but angular momentum and turbulence prevent steady collapse into the very centre, so the inflow becomes intermittent. The CMZ seems to form stars episodically rather than continuously, as if it must reach a threshold before it can ignite, Some models suggest a cycle where gas accumulates, becomes unstable, forms stars, then is disrupted by feedback that resets the conditions. The Milky Way's centre may breathe in bursts, not in a smooth inhale. The physics of that cycle is a balancing act, and the balance is not gentle. Gravity tries to gather gas into denser clumps, while turbulence and magnetic pressure resist compression, keeping clouds puffed up and supported. Shear can tear clouds apart, and tidal forces raise the threshold for survival, meaning only the densest clumps can remain bound. When collapse finally wins, it can happen quickly, producing clusters and massive stars that burn hot and die young. Then the newly formed stars push back, reheating and dispersing the gas that fed them, and the cycle begins again. Episodic star formation leaves timing clues, and the clues are written into stellar ages and gas structures. Young clusters near the centre suggest recent activity, while other intervals look comparatively quiet, as if the reservoir is waiting. Feedback from massive stars, winds, and supernovae can stir and heat the gas, delaying the next collapse by raising pressure and turbulence. Tidal forces are strong, raising the density threshold for a cloud to survive in the first place. The result is a star formation environment that looks inefficient despite abundant gas. That inefficiency is one of the centre's most revealing contradictions, because it breaks rules that work elsewhere. In the disk, more dense gas usually means more star formation, following empirical scaling relations that link gas surface density to star formation rate. In the CMZ, the gas is plentiful, yet the star formation rate is lower than naive expectations, as if the engine is flooded but refuses to start. Something is regulating the conversion of gas into stars, and the regulator is not a single knob. The regulation is not gentle, it is violent, turbulent, and time variable. Then comes the paradox of youth, which feels almost like a narrative twist because it violates the setting's logic. Very young, massive stars exist within the central parsec, where tides should hinder normal cloud collapse, and where radiation fields are intense. Some are arranged in a disk-like configuration, implying a common formation event rather than random capture. Their spectra reveal hot, luminous stars with short lifetimes, meaning they must have formed recently, not drifted for billions of years. Their presence demands either in situ formation under extreme conditions or delivery by migration. Both options are difficult, which is why the paradox persists. The visuals here are striking, and they reward a slow pan across the infrared field. Against the crowded background, the young stars stand out as bright blue-white points in false colour, their glare cutting through the dust-reddened crowd. Their orbits, when reconstructed, show partial alignment, like a tilted ring of motion wrapped around the invisible centre. It is as if a miniature stellar system formed inside the galaxy's most hostile neighbourhood, then kept its coherence despite constant perturbations. The question is not whether they exist, it is how they were allowed to. In situ models invoke a massive gas disk around the black hole that became self-gravitating, a temporary structure that changed the rules. If the disk was dense enough, it could fragment into stars despite tidal shear, because its own gravity would compete with the black hole's differential pull. That would naturally produce a coherent stellar disk and a bursty age distribution, matching what the orbits suggest. The disk would have to cool efficiently, shedding heat through radiation to allow collapse, which constrains its opacity and composition. In that scenario, star formation is not impossible, it is conditional, requiring a brief window when gas became both dense and cold enough. Migration models invoke clusters forming farther out and spiraling inward via dynamical friction, turning orbital energy into heat in the surrounding stars. Those clusters must survive tidal stripping long enough to deliver young stars, which is a stringent requirement in a steep potential. As a cluster falls inward, the galaxy's tidal field peels off its outer stars like bark from a tree, leaving a shrinking core. Only a very dense core could reach the central parsec intact, and even then it must arrive quickly enough that its massive stars are still alive. The model is elegant, yet it demands extreme initial conditions. The paradox matters because it ties star formation to black hole feeding, linking bright youth to dark appetite. If a dense gas disk formed stars, it also implies substantial gas reached the inner parsecs, at least briefly, and that gas could have fed Sagittarius A more strongly in the past. The centre's stellar ages become indirect probes of accretion history, like tree rings in a violent climate. The Milky Way's quiet black hole may be quiet only in the present tense. The past may have been louder than we expect. This is a recurring theme in galactic nuclei, and it is one reason the centre feels like a living system rather than a static object. Star formation and accretion compete for the same raw material, and each can regulate the other through feedback and consumption. A burst of star formation can consume gas and drive winds that starve the black hole, while also stirring turbulence that delays future inflow. Conversely, inflowing gas can both feed the black hole and build a disk dense enough to fragment, producing stars as collateral. The centre is a negotiation between building stars and feeding darkness. High-energy observations reveal a different centre than infrared star counts, and the contrast is almost cinematic. X-ray telescopes find a crowded field of compact objects and hot plasma, where the sky looks peppered with flickering points. In X-ray images, the nucleus glows with diffuse emission, punctuated by point sources that flare and fade, sometimes on timescales of hours. X-ray binaries flare as matter accretes onto neutron stars and stellar mass black holes, releasing gravitational energy as heat and radiation. Their distribution hints at how many remnants are packed into the nuclear region and how often binaries survive encounters. The centre may contain a hidden population of compact objects that are mostly dark until they accrete. Accretion is a conversion of gravity into light, and it is one of nature's most efficient energy engines. Gas spirals in, heats up through friction and shocks, and radiates intensely before it disappears, often forming a hot disk and a corona of energetic particles. In X-ray binaries, the timescales are short enough that variability becomes a diagnostic tool, revealing disk sizes and magnetic processes. A flare can reveal the presence of a compact object even when the companion star is faint or obscured. The galactic centre becomes a census site for the dead remnants of massive stars. Pulsar candidates and magnetars add to the inventory, and they also expose the biases in our surveys. A magnetar near the centre shows that neutron stars can exist in this extreme environment, surviving both formation kicks and subsequent encounters. Magnetars are rare, with magnetic fields so strong they can twist and crack a neutron star's crust, producing bursts and glitches that act like seismic events. Pulsars are hard to detect there because scattering by ionized gas smears radio pulses, stretching sharp ticks into indistinct hums. That observational bias could hide many pulsars, distorting demographic estimates and leaving us unsure what we are missing. The absence of evidence becomes part of the evidence problem. This is a reminder that the centre is difficult not only physically, but observationally, because the medium fights the measurement. The same plasma that glows in radio and X-rays can also act like a distorting lens for radio pulses, introducing delays and broadening that worsen at lower frequencies. Signals that would be crisp elsewhere arrive stretched and blurred, and the smearing can erase periodicity entirely. Detection thresholds become a function of the medium, not just the source, which complicates population studies. The census depends on the fog we're trying to see through. Compact object demographics connect back to the galaxy's life cycle, because remnants are the fossil record of past star formation. Massive stars die quickly and leave remnants that accumulate where star formation was intense, and the nucleus has had many opportunities to build such a stockpile. Dynamical friction can also drag heavier objects inward over time, creating a mass-segregated cusp where dark objects dominate the inner mass budget. If a cusp exists, it affects gravitational wave event rates and stellar disruption probabilities, changing how often compact objects collide or merge. The centre is not only a place, it is a long-term sorting machine. Over billions of years, the nucleus becomes a repository, and the repository has a logic that favours the heavy. Stellar mass black holes and neutron stars can sink inward, while lighter stars are more easily scattered outward, exchanging energy in countless encounters. The result is a central region that may be richer in dark mass than it appears in starlight, even if the black hole dominates the total. That hidden population matters because it changes the odds of close encounters, captures, and disruptions. In the centre, probability is destiny. Sagittarius A itself is a weak accretor today, and the weakness is one of the most informative facts about it. Its luminosity is tiny compared with active galactic nuclei, despite ample gas in the broader CMZ and a steady supply of stellar winds nearby. The inflow rate drops sharply from hundreds of parsecs to the event horizon scale, as if the gas keeps finding reasons not to fall. Much gas may be heated, blown out, or stalled by angular momentum before it reaches the hole, and some may circulate in a hot, thick flow. The black hole's diet is controlled by messy astrophysics, not by simple availability. The faintness is informative because it points to a specific accretion regime rather than a simple shortage. If the black hole were fed efficiently, it would shine orders of magnitude brighter, transforming the nucleus into a beacon that would dominate the night sky in high-energy light. Instead, the accretion flow appears radiatively inefficient, meaning much of the gravitational energy does not emerge as light where we can easily see it. Some energy may go into heating ions, driving outflows, or inflating magnetic structures that store and release energy intermittently. The center is not starved of material, it is inefficient at swallowing it. Yet there are signs the black hole was brighter recently in cosmic terms, and those signs are written into nearby clouds like delayed photographs. Molecular clouds near the center show X-ray reflection features, like echoes of a past flare, because hard X-rays can penetrate and then fluoresce. The clouds act like mirrors, fluorescing in iron lines when illuminated by energetic photons, and the brightness changes as the illumination front sweeps through. The geometry and time delays suggest illumination that varied over decades to centuries, which is recent on galactic timescales. These echoes imply Sagittarius A had outburst far above its current level. The center keeps receipts stored in cold gas. The idea of an echo is visually powerful because it turns the surrounding medium into a time machine. A flare happens near the black hole, then its light races outward at the speed of light, invisible to us until it strikes something dense enough to respond. Years later, a distant cloud lights up, as if someone switched on a lamp inside it, then dims as the front passes. By mapping which clouds brighten and when, astronomers reconstruct the flare's timeline, using light travel time as a ruler. The nucleus leaves a time-stamped signature across its surroundings. Longer-term evidence points to even larger past events, and it expands the story far beyond the central parsec. Above and below the galactic plane rise the Fermi bubbles, giant lobes seen in gamma rays, extending tens of thousands of light-years into the halo. In all sky maps, the bubbles look like translucent wings, symmetric around the center, as if the galaxy exhaled into intergalactic darkness. Their edges are sharp in some maps, suggesting a coherent outflow or shock that maintained a boundary. The Milky Way has scars that reach far beyond the bulge. Gamma rays trace extreme processes, cosmic rays colliding with gas, or energetic electrons scattering starlight to higher energies through inverse Compton interactions. Either way, the bubbles require sustained power over long times, because their volume and height demand work against gravity and ambient pressure. Their size implies that whatever inflated them did not merely flicker for a day, or even for a century. It acted long enough to push material into the halo and shape it, leaving a structure that persists as particles cool and diffuse. The calm sky we see now may be the afterimage of violence. The bubbles connect to galactic chimneys and the disk, halo circulation, where energy and matter cycle between dense star-forming regions and the tenuous halo. Hot gas and cosmic rays can vent through low-density channels carved by feedback, and once a channel opens, it can guide subsequent outflows. In the inner galaxy, clustered supernovae could drive a starburst wind that inflates large lobes, pushing a hot, enriched flow upward. Alternatively, a past active phase of Sagittarius AI could have launched jets or wide-angle outflows, injecting energy more centrally, but with similar large-scale consequences. Both hypotheses can fit parts of the data, and neither is closed. Each explanation carries different implications, and those implications reshape how we interpret the center's recent past. A starburst wind would mean the CMZ once formed massive stars at a higher rate, producing many supernovae in a short period and building pressure that vented upward. A black hole outflow would mean the nucleus briefly resembled an active galaxy, with accretion converting mass into kinetic power that inflated the halo structures. The bubbles may even record a combination, stellar feedback preparing channels, and nuclear activity exploiting them, because nature often stacks mechanisms rather than choosing one. The center rarely offers single-cause stories. The competing explanations raise the chapter's tension, because both options imply a Milky Way that is less placid than it appears. If the bubbles are from black hole activity, the Milky Way recently behaved like a weak AGN, and our galaxy has a dormant engine that can wake. If they are from starburst feedback, the center recently formed stars at a higher rate than today, and the CMZ's quietness is temporary. Either way, the present calm is misleading, and the galaxy's core has a variable temperament. The question becomes not whether it can erupt, but how often it does. That question is not only academic, because outbursts can reshape the conditions for future star formation by heating gas and altering pressure. They can also redistribute metals, pushing enriched material into the halo and changing the chemical starting point for later generations of stars. Over time, repeated episodes can change the galaxy's inner structure, subtly modifying the balance between inflow and outflow. The center is small, yet its influence can be large because energy spreads more easily than mass. A quiet nucleus can still have a loud history. Accretion and feeding cycles become the organizing uncertainty because the center behaves like a system of thresholds rather than a steady pipeline. Gas inflow along the bar can pile up at resonances, then leak inward in episodes when shocks and instabilities remove angular momentum. Stellar feedback can alternately clear and compress gas, modulating inflow and changing how much reaches the inner tens of parsecs. Near the black hole, radiatively inefficient accretion can swallow little and expel much, turning inflow into outflow before it crosses the horizon. The center may spend most of its time quiet, punctuated by short, bright spikes. The cycle can be imagined as a sequence of gates, each one requiring a different physical process to open. The bar drives gas inward, but it stalls where orbits change character and where crowding creates shocks that dissipate energy. Shocks and collisions can remove angular momentum, and some gas loses enough to drift closer, forming streams and rings. A fraction moves inward again, but magnetic fields and turbulence can still hold it up, keeping it hot and thick. Only when enough gas crosses enough gates does the nucleus brighten, and the bright phase may end by blowing the gate shut. These cycles also affect the broader galaxy, because the center is connected to the disk through flows that carry energy and composition. Outflows can heat the inner halo, redistribute metals, and alter the pressure environment of the disk, changing how easily gas cools and settles. Cosmic rays and magnetic fields can carry energy far from the launch region, influencing regions that never saw the original explosion. Even modest nuclear activity can influence star formation by changing the central gas reservoir, which then changes what the bar can deliver next. The Milky Way's core is not isolated from its spiral arms, it is coupled through flows. That coupling is visible in structure, and it becomes clearer when we let the camera glide along the plane. Dust lanes along the bar look like dark strokes that converge toward the bulge, as if the galaxy has drawn arrows pointing inward. Gas streams curve and intersect, forming ridges where compression is strongest, and those ridges show up as bright molecular emission. The inner galaxy is not a static picture, it is a set of moving lanes, each one carrying mass and momentum. The center is where those lanes deliver material, and where some of it is sent back out. The central molecular zone shows the coupling in real time, because its gas is visibly organized by the bar's potential. Gas streams follow non-circular orbits shaped by the bar, and their intersections create shocks that can seed dense clouds. Shocks and shear create dust lanes and compressed ridges that can seed dense clouds. Yet turbulence remains high enough to delay fragmentation. Clouds can be massive yet reluctant to form stars, as if they are heavy but internally braced. The CMZ looks like a reservoir under stress, always close to change. In spectral line observations, the CMZ becomes a topographic map of velocity, where motion is layered along the line of sight. Different components overlap in position, separated by their Doppler shifts, so a single direction can contain multiple streams at different speeds. Some features appear as coherent streams, others as tangled knots where collisions and feedback may have stirred the gas. The gas is not simply there, it is moving, colliding and reorganizing, and the reorganization is the story. The center is a dynamical system, not a container. Unusual chemistry becomes a tracer of that stress, and the molecules act like labels on invisible processes. Molecules associated with shocks, high temperatures, and cosmic ray ionization appear more strongly than in typical disk clouds, indicating that energy is being deposited deep inside the gas. Line ratios reveal dense gas fractions and excitation conditions that challenge simple star formation laws, because the same density does not yield the same outcome here. The center does not obey the same scaling relations as the outer disk, which is a clue rather than a failure. A galaxy can contain multiple star formation regimes at once. Chemistry here is a forensic tool because it records conditions that may be transient in temperature and density. Shock tracers suggest that clouds are being slammed and compressed, not gently settling, and that the compression may be frequent. Complex molecules hint at warm, dense conditions where reactions proceed quickly, building larger species before ultraviolet light can destroy them. Elevated ionization points to cosmic rays or X-rays penetrating deep into clouds, changing how gas couples to magnetic fields. The CMZ is not just gas. It is gas with a history written into its molecular fingerprints. The nuclear star cluster adds another layer of complexity, because its density makes rare interactions statistically meaningful. Its stellar population includes old stars, evolved giants, and the young massive stars that should not be there, all sharing the same tight volume. In such densities, close passages can strip envelopes and alter stellar evolution pathways, producing stars that look older or younger than they should. Collisions can create unusual objects, and repeated interactions can reshape the cluster's core, changing its density profile over time. Tidal disruptions can occur when stars pass too close to the black hole, turning a stellar life into a flare. Each process is rare per star, but the densities make rare events more common. A tidal disruption is one of the center's most dramatic possibilities, and it is a reminder that the black hole is not only a mass but a hazard. A star approaches, and the black hole's gravity pulls harder on its near side than its far side, creating a tidal force that stretches the star. The star is elongated, then torn apart, and part of it can form a temporary accretion flow that radiates intensely before fading. The flare would be brief on cosmic timescales, yet bright enough to be seen across galaxies, announcing the event to distant observers. In our own nucleus, the signatures may be subtle, but the physics is the same. The center is therefore both the best measured and most enigmatic region, and that duality is what gives it its power. Stellar orbits give precise mass and distance, and relativity shows up in data points rather than in thought experiments. At the same time, feeding history, hidden populations, and past outbursts remain partly speculative, because the system is complex and time variable. The more precisely we measure, the more structure we uncover in what we assumed was simple, and the more exceptions we find to our own rules. Precision reveals complexity rather than closure. This is a deeper lesson about exploration, and it echoes through the history of astronomy. When the map was blank, the mystery was obvious, but it was also vague, and vagueness can be comfortable. Now the map is detailed, and the mystery becomes specific. Why is star formation episodic? Where is the missing inflow? What shaped the bubbles? And what regulates the black hole's appetite? The center answers one question and immediately asks three more, each one sharper than the last. Knowledge does not end wonder, it refines it. This is the Milky Way's dark heart in full, seen through the wavelengths that can reach it. It is a place where dust hides the scene, but infrared and radio still build a map, star by star and orbit by orbit. It is a place where a black hole's mass is known to high precision, but its long-term behavior is uncertain, and its past may be written in echoes. It is a place where star formation is both suppressed and strangely possible, and where youthful stars orbit where they should not exist. It is a place where gamma-ray lobes hint at violence, while today's nucleus whispers, and that whisper is itself provocative, because quietness can be a phase rather than a personality. How many times has Sagittarius A flared since the first humans looked up, and how many of those flares left no record we have yet learned to read? How many cycles of accumulation and release shaped the CMZ's chemistry and turbulence, turning gas into a stressed reservoir rather than a steady nursery? How many compact objects drift unseen, waiting for a brief meal to announce themselves, and how many have already merged in silence? The center is quiet now, but quiet is not the same as inactive. The center shows the Milky Way at its most extreme, but it is not the whole galaxy. We begin inside the bright disk, where dust lanes cut dark rivers through starlight. Then we pull back. The camera keeps retreating until the familiar spiral becomes a luminous coin, and the surrounding halo emerges as a faint, sprawling volume. Out here, the galaxy's edges are not an edge at all, but a gradient of debris. In that dim territory, fragile structures record collisions across billions of years. From Earth, the Milky Way can feel like a fixed ceiling of stars, as if the sky were a dome nailed in place. Yet cosmology treats it as an unfinished object, a mid-sized spiral still assembling and still trading matter with its surroundings. The apparent stillness is an illusion created by our short lives and our embedded viewpoint. If we could speed time up, the galaxy would look restless. Streams would unfurl, satellites would shear, and gas would slosh in slow tidal waves. Start with context, because environment sets the rules of growth and limits what a galaxy can become. The Milky Way belongs to the Local Group, a small gravitational society inside the expanding universe. It is a neighbourhood defined less by light than by gravity, and its boundaries are fuzzy because gravity fades gradually with distance. The Local Group itself rides within the larger cosmic web, where filaments and voids set the stage long before any single star ignites. The Local Group is dominated by two spirals, the Milky Way and Andromeda, also called M31. They are comparable in mass, and they share a common history of accretion that began when the universe was young. A third major member, Triangulum or M33, orbits within the same shared potential, smaller but still substantial. Even at this scale, the group is not a tidy solar system of galaxies. It is a shifting arrangement of orbits, tides, and long-term capture. Around these giants swarm dozens of dwarf galaxies, plus many more that are faint and hard to detect. Some are gas-rich and irregular, while others are dwarf spheroidals that look like pale, diffuse embers. Their orbits, gas content, and survival depend on tides, ram pressure, and dark matter. In a deeper sense, they are experiments run by nature. Each dwarf tests how small a galaxy can be and still hold itself together. The Local Group is not isolated, but it is dynamically coherent on these scales. Its members fall along filaments of the cosmic web, where dark matter guides the first drafts of structure. In simulations, those filaments appear like luminous threads when traced by galaxies, but the real scaffolding is invisible. Baryons, ordinary matter, follow the gravitational wells carved by dark matter, cooling where they can and forming stars where conditions allow. This matters because galaxies do not grow only by making stars in place. They grow by accreting gas, capturing satellites and reshaping their disks through repeated gravitational encounters. A spiral's graceful arms can hide a violent biography, because the disk is only the current arrangement of matter. The halo, by contrast, preserves older chapters, written in faint star counts and subtle motions. Introduce the Milky Way's halo as the stage for this history. The halo is diffuse and extended, filled with old stars, globular clusters, hot gas, and dominant dark matter. Its visible component is thinly populated, so thin that the night sky does not reveal it directly. Yet its mass is enormous, and it sets the orbits of everything else. If the disk is the city of lights, the halo is the dark countryside that determines the city's borders. In the halo, time stretches, because orbital periods are long and densities are low. A star far from the centre can take hundreds of millions of years to complete a circuit. That makes the halo a museum of debris, where ancient events can remain legible. The museum is not curated, though, and its exhibits overlap. Streams cross streams, and old remnants blur into a background that still carries statistical memory. Satellite galaxies are the most obvious clues, because they are still intact. They are not just companions, but test particles that trace the Milky Way's mass and shape. Their trajectories respond to the total gravitational potential, including the disk, the central bulge, and the dark halo. When we measure satellite motions, we are effectively weighing the galaxy with orbiting clocks. The brightest satellites are the large and small Magellanic Clouds, visible to the naked eye from southern latitudes. In a dark sky, they look like detached pieces of the Milky Way, like luminous fog caught in the outskirts. They are dwarf irregular galaxies, gas-rich and actively forming stars. Their irregular shapes are not a sign of youth, but of disturbance. Small systems are easily warped by tides. The Large Magellanic Cloud is massive enough to matter dynamically, not merely photogenically. Its stellar mass and dark halo make it a significant perturber, closer to a minor galaxy than a trivial satellite. Its gravity tugs the Milky Way and can perturb the outer disk and halo. In precise measurements, even the Milky Way's centre of mass shifts slightly in response, an elegant reminder that gravity is mutual. The small Magellanic Cloud is smaller, but it is entangled with the LMC through tides and past close passages. Their mutual interaction triggers star formation and strips gas outward, especially during near encounters. The SMC's structure shows signs of being pulled apart, with stellar populations stretched into asymmetric distributions. In that distortion, we can read the choreography of their recent history. Their most dramatic signature is the Magellanic Stream, A long ribbon of neutral and ionized hydrogen trailing across the sky. It arcs for more than 100 degrees, a structure so large that it is difficult to grasp without an all-sky map. It is a gaseous tail shaped by tides and by interaction with the Milky Way's halo gas. Parts of it are cold and neutral, while other parts are ionized and warmer, revealing multiple phases of the same displaced material. Visually, the stream is not a bright object in ordinary light, so we imagine it through radio maps. In those maps, hydrogen glows at 21 centimeters, and the stream becomes a pale, winding brushstroke. It looks like a wake behind a ship, except the ship is a pair of galaxies, and the ocean is the circumgalactic medium. The stream's leading arm reaches ahead, hinting that stripping can throw material both backward and forward along an orbit. The stream shows that the Milky Way is not a closed system with a clean edge. Gas is exchanged and removed, then recycled or lost, depending on heating and mixing. Some of that gas may eventually cool and rain onto the disk, while some may be shredded and absorbed into the hot halo. The fate depends on density contrasts, magnetic fields, and how efficiently turbulence mixes cold clumps into warmer surroundings. The Magellanic System also challenges simple satellite models. Proper motions suggest the clouds may be on their first infall, which changes how we interpret their tails and orbital history. If they have not orbited many times, then the stream cannot be explained as a slow accumulation over countless passages. Instead, it becomes a snapshot of a relatively recent dramatic interaction, one that is still unfolding. If the LMC is a recent arrival, then its influence is a current event, not an ancient one. Its weight can stir halo material and bias measurements of the Milky Way's total mass. Even the distribution of other satellites may be affected, because a massive infalling companion can drag smaller systems along. The local group in that sense is not a calm hierarchy. It is a set of coupled motions where one newcomer can rearrange the apparent order, shift from living satellites to a satellite in the act of dying. The Sagittarius dwarf galaxy is being torn apart as it plunges through the Milky Way. It is an ongoing demonstration of tidal disruption, happening on timescales long for us but short in galactic terms. Each passage through the disk and inner halo strips more stars. Each passage also injects energy into the Milky Way's own structure. Sagittarius is a dwarf spheroidal, low in gas and dominated by older stars. It is stretched by tides into streams that wrap around the galaxy like a loose, stellar ribbon. Those stars do not leave randomly. They escape through regions near the satellite's tidal boundary, where the Milky Way's gravity overcomes the dwarf's self-gravity. Once freed, they continue along similar orbits, forming coherent arcs across the sky. Those Sagittarius streams are not decorative arcs, but dynamical evidence. Their positions and velocities encode the gravitational potential they have travelled through. When we map the stream in distance, sky position and motion, we're effectively tracing the shape of the Milky Way's invisible mass. The stream is a measuring tape made of stars stretched across the halo. A stream forms because a satellite's stars escape with similar energies and angular momenta. Over time, differential orbital motion stretches that escaped population into a coherent, thin structure. The leading arm runs ahead on a slightly different orbit, while the trailing arm falls behind. In a perfectly smooth potential, the stream would remain narrow for a long time. In a lumpy or time-varying potential, it thickens and develops wrinkles. Streams precess, fan out, and develop density variations as they orbit. The details depend on the Milky Way's dark matter halo shape, including flattening and possible triaxiality. Even a modest deviation from spherical symmetry changes how orbital planes rotate over time. That rotation leaves a signature in the stream's track, like a compass needle slowly drifting as it crosses uneven terrain. This returns to the earlier promise that motion is the honest language of mass. If the halo were perfectly spherical, stream planes would behave differently than if the halo is flattened or twisted with radius. The disk itself adds a symmetry, and the central bar adds time dependence, because it rotates and redistributes angular momentum. In practice, the Milky Way's potential is a layered object. Disk, bulge, bar, halo, and external perturbers all contribute. Sagittarius has been used as a lever on this problem, but the answer is still contested. The halo may be close to spherical in some regions, yet more complex when disk, bar, and LMC effects are included. Different datasets emphasize different parts of the stream, and different models make different assumptions about how the Milky Way has changed with time. The uncertainty is not a failure of measurement alone. It is a reminder that the galaxy is not static while the stream evolves. Streams also carry scars, and those scars are potential dark matter tests. Gaps and wiggles can be produced by dark subhalos, but also by ordinary perturbers like molecular clouds and the galactic bar. A close encounter with a compact mass can kick a segment of a stream, creating an underdensity that grows with time. The challenge is that baryonic structures can mimic the same effect, particularly in the inner galaxy. The detective story is therefore constrained by degeneracy. We need multiple streams, multiple radii, and full phase space information to separate exotic substructure from known baryonic disturbances. We also need careful forward modelling, where we simulate streams in realistic Milky Way potentials and compare them to data. The goal is not a single perfect stream fit. The goal is a consistent halo model that explains many traces at once. Gaia changes the scale of what is possible because it turns the sky into a kinematic laboratory. Gaia measures positions, parallaxes, proper motions, and photometry for over 1 billion stars. The mission's precision is so high that tiny angular motions become measurable, even for stars thousands of light years away. In effect, Gaia gives the Milky Way a pulse, because it reveals motion everywhere. With radial velocities for many stars, Gaia builds 6-dimensional phase space for a large subset. That means we can map not only where stars are, but how they move through the Milky Way. 6 dimensions sounds abstract, but the meaning is simple. A star's location and its velocity together define its orbit. Once you have orbits, you can infer the gravitational field that shapes them. This is the revolution of galactic archaeology, because merger debris remains clumped in velocity space longer than in position. Even when stars are spatially mixed, their motions can reveal a shared origin. The halo, in particular, is a place where ancient groups dissolve slowly. A disrupted dwarf stars can spread across the sky and still retain a recognizable velocity pattern. Gaia makes those patterns visible, turning the halo into a searchable archive. Gaia revealed a major ancient collision through a distinctive kinematic signature. The debris is often called Gaia sausage or Enceladus, reflecting its elongated velocity distribution, an inferred progenitor. The sausage description is not poetic exaggeration. In velocity space, the distribution looks stretched, indicating stars on highly radial orbits. Those orbits are the hallmark of a massive object plunging in and being shredded. The key point is scale, because this was not a minor snack. Models suggest a massive dwarf galaxy merged with the Milky Way roughly 8 to 11 billion years ago. That timing places it after the earlier star formation, but early enough to reshape the young galaxy. It likely arrived when the Milky Way's disk was still forming, when gas fractions were higher, and the structure was more easily heated and thickened. That merger likely contributed a large fraction of the inner stellar halo. It also heated the early disk, helping build the thick disk population introduced in earlier chapters. Heating here means increasing the random motions of stars, puffing the disk up vertically. A single major merger can do this, but repeated smaller encounters can also contribute. Gaia Enceladus provides a concrete candidate for a dominant event in that era. The collision left behind stars on radial, plunging orbits, unlike the more circular disk. Their chemistry is distinct, typically more metal-poor and with different alpha element patterns. Those abundance patterns are a record of star formation speed. Rapid star formation enriches gas with alpha elements from core collapse supernova, while slower histories allow more iron from Type Ia supernovae to accumulate. Dwarf galaxies, with their lower masses, often follow the slower track. Gaia also reveals other substructures, including smaller accretion events and phase space clumps. Some of these appear as coherent moving groups, while others show up as ripples in the disk's velocity field. The halo is not smooth, but layered, like overlapping footprints from multiple infalls. Each footprint has its own orbital shape and chemical palette. Together, they form a composite portrait of hierarchical growth. This reframes the Milky Way as a cannibal galaxy in a standard cosmological model. In lambda CDM, galaxies grow hierarchically, assembling from smaller building blocks over time. The model's success on large scales is striking, but the Milky Way lets us test it at intimate resolution. We are not looking at a distant statistical sample. We are reading a single system in forensic detail, from the inside. The Milky Way's halo is therefore expected to contain many remnants. The surprise is not that mergers happened, but that we can identify specific ones from inside the system. For decades, astronomers suspected the halo was built by accretion, but the evidence was diffuse. Gaia turned suspicion into catalogued substructure. It also raises a question that is almost philosophical. How many distinct ancestors does our galaxy contain, and how many have been erased beyond recognition? Globular clusters enter as another class of clues because they are ancient and compact. They are dense star clusters orbiting in the halo, bulge, and thick disk. In images, they look like tight spheres of starlight, with bright cores and faint halos of their own. They are gravitationally bound systems that can survive for a Hubble time. That longevity makes them valuable witnesses. Many globular clusters are extremely old, with ages around 10 to 13 billion years. They formed near the beginning of the Milky Way's history before the disk looked like it does today. Some may even predate the final assembly of the Milky Way's main body, forming in smaller progenitors that were later accreted. Their ages are measured through stellar evolution models, using the turn-off point where stars leave the main sequence. That method is technical, but the result is clear. These clusters are among the oldest luminous structures we can study. Their stars are chemically informative because they preserve early abundance patterns. Their metallicities span a wide range, from very metal-poor to relatively enriched. Metallicity in astronomy is a proxy for generational depth. Low metallicity implies formation from gas that had experienced few previous supernovae. Higher metallicity implies a longer chain of enrichment. In globular clusters, those chains can be short but intense. Globular clusters also have distinctive internal chemistry, including multiple stellar populations. That complexity suggests early self-enrichment and unusual formation conditions in dense environments. Some clusters show variations in light elements that imply multiple episodes of star formation or complex processing of gas. The details remain debated, but the implication is important. These are not simple, single-burst objects. They are laboratories of early chemical evolution. Their orbits are especially valuable because clusters behave like long-lived test particles. Some clusters have retrograde orbits or high eccentricities that hint at accreted origins. A retrograde orbit suggests formation in a system with a different angular momentum direction, later captured by the Milky Way. High eccentricity suggests a history of infall rather than in-place formation in a settled disk. When combined with chemistry, orbit becomes a fingerprint. Several globular clusters appear linked to known merger events, including Sagittarius and Gaia Enceladus. Their association is inferred from shared orbital planes, energies, and chemical properties. In Sagittarius, for example, clusters can ride along with the stream, like beads on a torn necklace. In Gaia Enceladus, clusters share the same radial bias in their orbits. These links are not always definitive, but they are increasingly persuasive as data improve. This is a key narrative beat, because it connects small objects to big history. A globular cluster is a fossil that can tag a lost galaxy, even after the parent system is shredded. It is also a reminder that accretion is not only about adding field stars, it is about importing whole subsystems, clusters, dark matter, and chemical histories. Each imported cluster is a compact archive, carried intact across cosmic time. Now widened from clusters to the diffuse stellar halo itself. The halo is a sparse population of stars extending far beyond the disk, with low metallicity on average. In a visualization, the disk is a bright plane, while the halo is a faint, roughly spherical glow. But even that is an oversimplification, because the halo is structured. It contains streams, shells, and gradients that reflect how it was assembled. Halo metallicity shows gradients and substructure, reflecting mixed origins. Inner halo stars can be more metal-rich than outer halo stars, consistent with multiple accretion pathways. Massive progenitors sink deeper through dynamical friction and deposit more enriched stars closer in. Smaller, more primitive systems contribute to the outer halo, where the gravitational field is weaker and mixing is slower. The halo is therefore stratified, not just spatially but chemically. Chemistry becomes a second coordinate system, alongside motion. Element ratios act like timestamps, because different supernova channels enrich gas on different timescales. Core collapse supernovae happen quickly, within tens of millions of years, while type Ia supernovae can take 1 billion years or more. That delay changes the ratio of alpha elements to iron. In plain terms, chemistry tells us whether a system forms stars fast or slow. Alpha elements relative to iron can distinguish rapid enrichment from slower, delayed enrichment. Dwarf galaxies often show lower alpha at a given metallicity, reflecting extended star formation histories. They form stars inefficiently, and their shallow gravitational wells allow gas to be blown out more easily. That means fewer massive stars exploding early, and more time for delayed ion enrichment to accumulate. When those dwarf stars are accreted, they bring that chemical signature into the halo. This allows chemical tagging, the attempt to reconstruct lost systems by matching detailed abundance patterns. The method is powerful in principle, but challenged by mixing and by overlapping chemical tracks. Two different progenitors can produce similar alpha to ion ratios, especially if their star formation histories converge. The strongest tagging uses many elements at once, building a multi-dimensional chemical fingerprint. Even then, uncertainties remain, which is why combining chemistry with kinematics is so effective. The halo offers a cleaner arena than the disk, because it is less chemically homogenized. Accreted stars can retain distinct abundance signatures longer, especially at low metallicity. The disk, by contrast, experiences ongoing gas inflow and mixing, which blurs chemical distinctions. In the halo, the low density and long orbital times allow substructures to remain coherent. That coherence is why the halo is so valuable for archaeology. Rare stars add sharper clues, including R-process-enhanced stars enriched in heavy elements like europium. Their abundance patterns point to rapid neutron capture, a process that requires extreme conditions. The leading candidates include neutron star mergers and certain rare supernova channels. These events are uncommon, but their yields can be enormous. When they occur in small systems, their chemical imprint can dominate. Because dwarf galaxies have small masses, a single R-process event can dominate their heavy element budget. When such a dwarf is accreted, its stars carry that extreme signature into the Milky Way halo. In a survey, these stars stand out like bright dye in clear water. They are not just curiosities, they are evidence that early chemical enrichment was patchy, with localized events imprinting small regions of gas. This connects to earlier questions about R-process sources and mixing times. The halo suggests inhomogeneous enrichment early on, with chemical patches that were later assembled into one galaxy. How quickly did metals mix in the first small galaxies, and how often did rare events occur? Those questions are not abstract. They determine how we interpret the oldest stars as records of the first generations. The Milky Way, assembled from many pieces, becomes a composite sampling of early cosmic chemistry. The Milky Way's hidden history is therefore written in two scripts at once. One script is kinematics, the other is chemistry, and the strongest conclusions come when both agree. When a group of stars shares an orbit and a chemical pattern, the case for common origin becomes compelling. When they disagree, the tension is informative. It can reveal later dynamical heating or chemical overlap between different progenitors. Either way, the galaxy becomes readable. Introduce the missing satellites problem, because it tests the cosmological model at small scales. Simulations of cold dark matter predict many more low-mass subhalos than the number of observed dwarf galaxies. In the language of theory, the Milky Way should be surrounded by a swarm of dark matter clumps. Yet the sky shows far fewer luminous dwarfs than the simplest predictions. The discrepancy is not enormous on a log scale, but it is conceptually sharp. This mismatch can be framed as a census problem, not necessarily a physics failure. Many subhalos may be dark, having formed few stars, making them hard to detect. A halo without stars is nearly invisible, except through its gravitational influence. It might reveal itself by perturbing a stellar stream, or by subtle lensing effects, or by the dynamics of gas. The question becomes practical. How do you find what does not shine? Feedback is one proposed solution, because supernovae and stellar winds can remove gas from shallow potentials. If gas is expelled early, star formation can be suppressed, leaving a dark halo behind. In small dwarfs, the escape velocity is low, so a few energetic events can have outsized consequences. Feedback also changes the internal structure, potentially flattening central density profiles. That possibility links dwarf counts to the detailed physics of star formation. Reionization is another proposed solution, because the early universe became bathed in ultraviolet radiation. That background can heat gas and prevent it from cooling into the smallest halos. Reionization is a global event, occurring when the first stars and galaxies ionize the intergalactic medium. Afterward, gas had a harder time collapsing into tiny gravitational wells. The smallest halos may have formed stars briefly, then been shut down, becoming fossil systems with ancient populations. Dark matter physics itself may also matter, if dark matter is warmer or self-interacting. Such models can reduce small-scale structure, but they must still match large-scale successes. Warm dark matter suppresses the formation of the smallest halos by smoothing early density fluctuations. Self-interacting dark matter changes how halos evolve internally, potentially affecting satellite survival. These ideas are constrained by many observations, so the missing satellites problem becomes a careful balancing act rather than a single decisive test. Observations have improved the dwarf census, especially with deep surveys finding ultra-faint dwarfs. Yet incompleteness remains because the faintest systems are easiest to miss behind the disk. Ultra-faint dwarfs can contain only a few thousand stars, spread over a large area, making them hard to distinguish from foreground populations. Their discovery often requires sophisticated statistical searches for subtle overdensities. Each new dwarf found reduces the tension, but also raises new questions about how many remain unseen. The missing satellites problem therefore becomes a measurement frontier. It pushes us to map the sky more completely and to model selection effects honestly. It also pushes theory to include realistic baryonic physics, not just dark matter. In that sense, the problem is productive. It forces a dialogue between simulations and surveys, between what should exist and what we can actually detect. Return to gas because growth is not only stellar cannibalism. The Milky Way also accretes gas from its surroundings, and that gas sets the future star formation budget. Stars lock baryons away for billions of years, but gas is the flexible currency of evolution. Without fresh gas, star formation declines as the disk consumes its supply. So the question becomes, where does the next generation of gas come from? The circumgalactic medium, or CGM, is the Milky Way's extended atmosphere of hot and warm gas. It is difficult to image directly, but it reveals itself through absorption lines, an X-ray emission. The CGM extends far beyond the visible disk, possibly out to the virial radius, where the galaxy's gravity still dominates. It is not uniform. It contains hotter diffuse plasma, cooler clouds, and interfaces where mixing and conduction occur. Ultraviolet absorption against background quasars detects ions like OV tracing warm-hot gas. In spectra, those ions appear as narrow dips at specific wavelengths, a subtle signature of material between us and a distant beacon. X-ray observations detect hotter components, suggesting a massive reservoir at millions of degrees. At those temperatures, gas does not glow brightly in visible light, but it can emit in soft X-rays and imprint absorption on X-ray sources. Together, UV and X-ray data reveal a multi-temperature halo. This hot halo can contain a significant fraction of the galaxy's baryons. It also acts as a buffer, receiving outflows from the disk and feeding inflows back over long times. Inflows can be slow, mediated by cooling instabilities and condensation. Outflows can be episodic, driven by clustered supernovae and stellar feedback. The CGM is therefore not simply a storage tank. It is a dynamic interface between the galaxy and intergalactic space. High-velocity clouds are another piece of the accretion story. They are neutral hydrogen clouds moving at speeds inconsistent with simple disk rotation, some likely falling toward the disk. In radio maps, they appear as isolated patches with distinct velocities, sometimes with comet-like shapes. Their origins are mixed, which is part of their interest. Some are likely returning fountain material, while others may be external infall. Some high-velocity clouds may be condensations from the CGM, cooling and raining back down. Others may be tidal debris from satellites, including the Magellanic System. The difference matters because it tells us whether the Milky Way is fed mostly by recycled gas or by fresh external supply. Cooling depends on metallicity and density, because metals radiate energy efficiently. A metal-poor cloud can remain hot longer, delaying its contribution to star formation. The CGM is therefore both supply and sink, and it complicates the idea of a clean galactic boundary. The Milky Way's star formation depends on how efficiently this halo gas can cool and settle. If the CGM stays too hot, the disk slowly starves. If it cools too efficiently, star formation can surge, potentially triggering stronger feedback that reheats the halo. The system tends toward balance, but the balance can shift with mergers and environmental changes. This also links back to feedback from earlier chapters. Supernova-driven winds and cosmic rays can push gas into the halo, where it may later return in a galactic fountain. The fountain is not a simple loop. Gas can mix with halo material, change phase, and return with altered angular momentum. That mixing can dilute metals and redistribute them, influencing the chemical evolution of the disk. The halo, in that sense, is part of the disk's long-term metabolism. The Milky Way's evolution is a balance between inflow and outflow. Mergers add stars and dark matter, while gas accretion and recycling determine how long the disk can keep forming new stars. When we talk about a galaxy growing, we're really talking about multiple coupled processes. Some add mass, some rearrange it, and some regulate the conversion of gas into stars. The halo is where these processes meet, quietly but decisively. Now raise the stakes with the future collision, because the local group is not static. Andromeda is approaching the Milky Way at roughly 110 kilometers per second along the line of sight. In the night sky, M31 is a faint smudge to the naked eye, but in reality it's a massive spiral with its own satellites and halo. Its approach is measured through Doppler shifts, a subtle change in spectral lines that reveals motion toward us. The fact that it is coming closer means local gravity is winning over cosmic expansion on these scales. Proper motion measurements suggest the encounter is not a clean head-on hit, but a complex orbital dance. Even so, simulations predict a merger timescale of about 4 to 5 billion years. That timescale is comparable to the remaining main sequence lifetime of the Sun, which gives the event a strange intimacy. The details depend on the transverse velocity, the mass distributions, and the dynamical friction between their halos. Even a near miss can lead to eventual capture, because energy is dissipated into the surrounding dark matter. The first close passage will distort both disks through tidal forces. Tails and bridges of stars and gas will form, and star formation may flare as gas is compressed. In a visualization, the disks stretch like taffy, throwing arcs of material into intergalactic space. Those tails are not just pretty, they are a mechanism for redistributing angular momentum and for feeding the future remnant. Some material may be flung outward and later fall back, building shells and extended halos. Over subsequent passages, dynamical friction will drain orbital energy. The two galaxies will coalesce into a single remnant, likely an elliptical-like system, with a more spheroidal stellar distribution. The remnant will not be a perfect elliptical in the classical sense, but a relaxed system with less obvious spiral structure. The disk's ordered rotation will be partially converted into random motions. Dust lanes may persist for a time, but the long-term morphology will be smoother and rounder. Their central black holes will eventually form a binary and merge, emitting gravitational waves. The details depend on gas, stellar scattering, and how efficiently the binary hardens. In the final stages, gravitational radiation carries away energy, allowing the black holes to coalesce. That event would be among the most energetic in the local group, though it would be invisible to human eyes. It would be heard, in principle, by future gravitational wave observatories tuned to low frequencies. The Sun's fate is not direct destruction, but relocation. Simulations often place the solar system farther from the remnant's centre, though outcomes vary with orbital details. The Sun is a tiny test particle in this drama, unlikely to collide with another star because space is vast. Yet its orbit can change dramatically as the gravitational potential rearranges. The night sky from Earth, if Earth still exists, would be unrecognizable. New constellations formed by tidal debris and the bright core of Andromeda swelling across the sky. This future event reframes the Milky Way's identity. Our galaxy is not a permanent spiral, but a phase in a longer sequence of assembly and transformation. The Milky Way we know is a snapshot, not a final form. The same physics that built the halo streams will, eventually, erase the disk's current symmetry. In a larger sense, the local group will become a single dominant remnant, with smaller satellites either absorbed or flung outward. Bring the narrative tension to the front because it is the chapter's climax. The Milky Way feels stable on human timescales, yet it is built from fragments and still absorbing new ones. The halo's streams show ongoing disruption in real time. Gaia's debris fields show that even the thick disk and inner halo carry the memory of a violent ancient collision. The galaxy's calm face hides a continuing process of assembly. The Magellanic Stream shows gas being stripped and redistributed today. The CGM shows a hidden reservoir that can either fuel the next era of star formation or remain too hot to use. The missing satellites problem reminds us that much of the local group may be invisible. The galaxy's growth may involve dark companions that leave only gravitational fingerprints. Each of these lines of evidence points to the same conclusion. The Milky Way is porous, interactive, and unfinished. This returns to the central question, because we still map the Milky Way from inside its dust and darkness. We infer its past from motions and chemistry, and we infer its mass from how others orbit it. Our perspective is both a limitation and an advantage. We cannot see the galaxy as a whole in one glance, but we can measure individual stars with exquisite precision. From that precision, we build a global model, piece by piece. We cannot step outside to take a photograph, so we build a narrative from clues. Streams, clusters, dwarfs, and hot gas become the evidence, and gravity becomes the judge. The judge is impartial, but the evidence is incomplete because selection effects and dust obscure parts of the sky. That incompleteness is not discouraging. It is the reason the story remains alive, because each new survey opens another window, transition. After tracing a past built by mergers and a future headed toward merger, we return to the human question. What does it mean to know a galaxy from within, and what mysteries remain unsolved? The Milky Way is both our home and our laboratory, and those roles can conflict. We want a coherent picture, but the galaxy offers only partial views. The most honest approach is to treat our models as evolving, like the system they describe. Set up the final chapter by narrowing the uncertainty. The next frontier is combining all traces into one self-consistent model, including dark matter shape, baryon cycling, and time-variable structure. That means fitting streams and satellites while also matching the disk's dynamics and the CGM's mass. It means accounting for perturbers like the LMC, whose influence is not negligible. It also means embracing time dependence, because the Milky Way is responding to infall right now. End on a controlled ambiguity, because mystery is the tone. The Milky Way is a living system, but we only see its life through partial windows, and the windows are finally widening. As we widen them, we may find that the halo is more structured than we imagined, and that the boundary between galaxy and environment is more permeable than our language suggests. The deeper question lingers: how many of the Milky Way's ancestors are still detectable, and how many have dissolved into anonymity? We return to the central question: what is the Milky Way when we observe it from inside dust and darkness? From Earth, the galaxy is not a clean spiral on black velvet, but a luminous river, broken by soot lanes, stitched with star clouds, and bent by perspective. The whole galaxy is one gravitational narrative, written in orbits rather than ink. A thin, star-forming disk rides inside a thicker, older disk, where stars move with larger vertical excursions and carry the memory of early turbulence. The bulge and its boxy peanut shape reflect a bar that redistributes angular momentum, funneling gas inward and reshaping stellar paths over billions of years. The halo holds streams, globular clusters, satellites, and most of the mass, forming a vast, dim scaffold beyond the bright disk. Dark matter sets the rotation curve, stabilizes or distorts structure, and binds the system, its pull inferred from speeds that stay high where visible matter thins. Spiral arms remain a moving puzzle, partly because we live inside the pattern we are trying to draw. Some patterns behave like long-lived density waves, where gas compresses as it enters an arm and then drifts out again. Others look like transient segments, born from instabilities and sheared by differential rotation, with the inner galaxy lapping the outer like runners on different lanes. Gas shocks, star formation traces, and non-circular motions complicate every map we draw, especially when dust hides the very distances we need. Even the classic picture has a history. Astronomers argued for centuries about the Milky Way's shape before radio surveys and infrared views began to cut through the haze. Transition. To understand fate, we follow the fuel, not the starlight. Star formation declines because gas is finite, and conversion is inefficient, even in clouds that look thick enough to collapse. Supersonic turbulence stirs the gas, magnetic fields thread it like tensioned wires, and feedback injects heat and momentum that can unbind a nursery before it finishes its work. Stellar winds carve cavities, ultraviolet light strips electrons from hydrogen, and supernovae drive expanding shells that can both trigger and suppress the next generation. The circumgalactic medium may be the long-term reservoir, a faint halo of hot and warm gas extending far beyond the disk, but its mass and cooling rate remain uncertain. Without sustained inflow, the disk slowly quiets as molecular gas becomes scarce, and the bright blue signatures of youth fade from the spiral arms. In the far future, red dwarfs dominate the light, because the smallest stars sip their fuel with extreme patience. They burn slowly for trillions of years, long after massive stars vanish, and the galaxy's most brilliant beacons have already come and gone. The Milky Way's brightest era is temporary, but its faintest era is long, an extended twilight where the sky is steadier, dimmer, and less violent. Habitability is a galactic ecology problem, shaped by chemistry, radiation, and time. Metals enable rocky planets, so early epochs were poorer in building material, and the first disks likely formed with fewer solid grains to assemble worlds. Inner regions offer more metals, but also higher supernova rates and denser radiation fields, where energetic particles and ultraviolet light can erode atmospheres. Gamma-ray bursts are rare nearby, yet they remain a low-probability global hazard, a reminder that the galaxy is not uniformly gentle. The galactic habitable zone is a useful idea, but migration, shielding, and time dependence blur its borders. Stars drift, spiral arms come and go, and a safe neighbourhood can change over geological timescales. Open mysteries remain, and they are structural, not cosmetic, because they determine how the system actually works. Dark matter's particle nature is unknown, even as its gravity is measured everywhere, from stellar motions to the bending of streams. We still lack a definitive 3D dust map that turns extinction into a solved correction, because dust is clumpy, layered, and mixed with gas on many scales. The CGM's total baryon budget and mixing physics control the future fuel supply, deciding whether the disk can be replenished or must simply run down. The precise merger history is incomplete, because debris overlaps in phase space and chemistry, and ancient collisions can masquerade as one another in today's crowded data. Transition. The next decade is a tool change, not a theory change. Gaia continues refining distances, proper motions, and the galaxy's time-dependent kinematic substructure, turning the sky into a living map of streaming motions and resonances. JWST probes embedded star formation, stellar chemistry, and the earliest enrichment pathways, using infrared vision to see through dust where optical surveys go blind. The Vera C, Rubin Observatory maps transients, variable stars, and faint halo structure at scale, catching the galaxy in motion as it flickers and changes night after night. ESCA will trace hydrogen across the disk and into streams, linking fuel to dynamics and revealing how gas flows along bars, arms, and tidal debris. LISA will hear compact binaries in the Milky Way, turning gravity waves into a new census, an audio map of dense remnants orbiting in darkness. We are a moving point inside a rotating pattern, carried around the center once every few 100 million years. We decode radio whispers, infrared glows, and tiny stellar wobbles into a model we can test, and each new measurement tightens the story. The galaxy is not a picture we take, but a system we reconstruct, one spectrum, one parallax, one orbit at a time. So what is the Milky Way really? It is a barred spiral ecosystem, built by mergers, regulated by feedback, and dominated by invisible mass. We know it by patient measurement from within, and by insisting that motion and spectra are evidence, not decoration. The unknowns are not failures. They are frontiers that define the next map, and they keep the night sky intellectually alive. Final cadence. The Milky Way is a scientific object and a night sky presence. That ancient band of light is a map of where we live and a reminder that home is written in gravity. Across these 200 facts, the Milky Way stopped being a pretty band of light and became an engineered story of evidence. We traced a barred spiral with a thin, star-forming disk and a thicker, older one, a boxy bulge shaped by the bar, and a faint halo threaded with streams, globular clusters, and satellites. We watched dust rewrite the sky in visible light, then saw infrared and radio slip past that censorship, turning obscuration into a measurable foreground. We learned that distance is the first rung of every ladder, from Gaia's parallax to Cepheids, RR Lyrae, mass of VLBI, and the careful accounting of extinction. We followed motion as the galaxy's most honest language, using Doppler shifts, proper motions and rotation curves to weigh what starlight cannot carry. That single clue, flat rotation where light should thin, opened onto a dominant dark matter halo, a gravitational scaffold we still cannot see directly. We entered the interstellar medium as a living weather system, turbulent and multiphase, stitched by microgauss magnetic fields and energized by cosmic rays. We visited the star factories where cold molecular clouds fragment into filaments, where disks and jets solve angular momentum, and where feedback both triggers and throttles new suns. We counted the galaxy's chemistry as a memory, alpha elements and iron timing supernova histories, and rare R process signatures hinting at neutron star mergers and other explosive channels. We dropped into the inner parsec and found the clearest proof in the film, stars like S2 drawing tight ellipses that demand a 4 million solar mass black hole at the centre. We then pulled back to the Halos Museum, where Gaia revealed ancient collisions, including the Gaia-Enceladus merger that heated the disk and built much of the inner halo. And we looked forward to a future shaped by dwindling fuel, uncertain replenishment from the circumgalactic medium, and the coming tool change of JWST, Rubin, SKA, and LISA. The threads never separated, because structure, origin, hidden contents, and destiny are one problem seen from different angles. Spiral arms blur into transient segments under differential rotation, the bar talks gas inward and buckles the bulge, and external encounters warp the disk and seed streams that later become our measuring tapes. Even our most confident maps remain probabilistic because every line of sight stacks overlapping populations, and every tracer, stars, gas, dust lanes, sits slightly offset in time and space. Yet the same limitations that trap us inside the streets also give us leverage, because we can watch the traffic, measure the drift, and compare billions of stars against one another. So what is the Milky Way really, when we cannot step outside and take the photograph we crave? It is a living, evolving system, part luminous stars, part invisible mass, whose true shape emerges only through patient measurement, stitched together from distances, motions, chemistry, and the shadows dust leaves behind. We prove it from inside the dark the way you learn a city in a fog, by timing its rhythms, tracing its flows, and letting gravity reveal the streets you cannot see. The mystery is not that our map still has blank spaces, or that dark matter and dust keep their secrets with stubborn discipline. The deeper wonder is that atoms on one small world can reconstruct 100,000 light-year home at all, and still look up and find new evidence waiting in the same familiar band of night. If you want to keep travelling, follow the next data releases and sky surveys, and let the Milky Way's changing measurements reshape your picture of what home means.